Hi there, and in this course we'll be covering the topic of using Docker in real-world scenarios. First off, we'll look into deploying single service or monolithic applications. We'll connect databases and look into methods for backing up and restoring mission-critical data. Next, we'll look into optimizing the code to deployment workflow with continuous testing and deployment using Circle CI. After that, we'll start diving into some aspects of scaling web applications that have been historically difficult but have become drastically simpler with Docker. We'll cover service and microservice patterns and look how Docker greatly simplifies the process of breaking your application into separately scalable pieces that can all communicate with each other easily. Then for the big pieces, service discovery and dynamic architecture. Containerization allows us to make great improvements to the traditional architecture patterns of services and apps running on individual servers. Instead, we'll run services across dynamic clusters of servers and end up with an architectural pattern that's easy to scale to a very large capacity. And then finally, we'll look at deployment strategies in a container-driven environment. As you can see, we're going to cover a lot of ground that'll really make this course worth the time and effort that you put into it. The recommended tools for this course is a computer with Linux, Mac OS 10.8 or greater, and Windows 7 or greater that's 64-bit. And then you'll also want access to a computing infrastructure such as AWS, DigitalOcean, Rackspace, or so forth. Now, if you don't have access to one of these, AWS does have a free tier, DigitalOcean has an ongoing DO10 coupon code for $10 of credit, and Rackspace has a free tier as well. And either one of these should give you enough to get through this course just fine. That's about it. Let's get into this course and have a great time learning how to use Docker in the real world. Let's take a minute to talk about some of the advantages of building with Docker and container-based architecture. When most developers start using Docker, they quickly realize that it's a different paradigm from the traditional way of building and deploying applications. The advantages that you get, however, are very much worth the effort. Let's take a look at the advantages you get in the development environment. First of all, it's an isolated environment, which means there's a lot less machine setup. You simply install Docker, and your application container will run and run correctly because all the configuration lives inside of the container. This means that whether you're on Mac, Linux, or Windows, if Docker's installed, your containers will run. Also, you have an identical environment whether you're on development, staging, QA, or production, because all the environment is contained within the container. This really solves the problem of, it works on my machine, why doesn't it work on production? Another big advantage is that you only have to run one virtual machine on your development environment. If you're used to using Vagrant, you know that you have to have a separate virtual machine with Vagrant for every project you're working on. While for some developers working on one large project for a whole year, this may be fine. If a developer is working on a dozen projects, they have to have a dozen virtual machines taking up lots of hard drive space. That's not efficient. With Docker, you run the one Docker virtual machine and all your projects can run in containers on that machine. Now let's take a look at the production environment where some of our biggest advantages lie. The first advantage you get is immutable and disposable infrastructure. You have two pieces that are immutable, the servers and the containers. The servers are very dumb servers. They simply run Docker, which means it's easy to create more and it's easy to dispose of them and get rid of them. Also, your containers are immutable that run on the servers. Once a container has been deployed, you never change it, you never update it, you never modify it. You simply dispose of it and replace it with a new version of an updated container. Also, your infrastructure is very portable. Because everything an application needs to run is defined within the container, you can run that container anywhere you have a Docker environment, whether that's AWS, Google Container Engine, DigitalOcean, anywhere, as I said, where there's Docker. Scaling is also very simple. Do you need more web servers? Simply run more web servers. If you want your web apps to go from 5 to 25, you simply run 20 more web app containers across your server infrastructure. Applications can also be decoupled from individual servers with Docker infrastructure, which is a tremendous advantage. In the traditional model, there's one server per application. In the Docker infrastructure, however, servers are scaled and monitored separately from applications. You have a server cluster, which is scaled and monitored from more of an ops perspective, and then you have applications, which are scaled and monitored from more of a development perspective. This decoupling gives the developers on the team a lot of freedom that services like Heroku have traditionally offered, but they allow you the flexibility to manage your own infrastructure and build the architecture that your company truly needs. There's also a lot of potential for cost savings with Docker. Many applications don't consume 100% of the resources of the servers that they reside on. But with Docker, you can run multiple containers on one server and utilize those resources much more efficiently. Here's a visual example of a typical Docker production architecture. You have two main components, your server cluster and your application containers that are run across the servers. This is very often called scheduling. The server nodes are simply servers running Docker, so a container can run on any server. This allows the servers to be quickly and painlessly scaled up and down, as well as destroyed and replaced. This also means that once your server cluster is in place, your application developers don't have to be concerned with servers anymore. They build applications and they simply run them on your server cluster. If you start running out of resources, then you can add more servers to the cluster. Lastly, let's talk about testing environments. One of the first big wins in testing is that you can test production containers before deploying them. When you build your production container, you can run a test suite within it to make sure that it's running as expected. When your container is ready to go, you can then deploy the exact container you just ran the tests in. Also, it's easy to create identical environments. While the production server cluster may contain anywhere from dozens to thousands of server nodes, you can quickly spin up a testing or QA environment with one or two nodes, and then run the exact same production containers on it. Also, the code for an entire environment can live in a single simple Docker file, so there's no need for complicated and slow provisioning scripts anymore. And lastly, containers are dynamically configurable, which means that every value that could differ across environments, say a database host, it's configurable within environment variables. So you can reuse one container across multiple environments. Your production container can also be used in staging, and it can also be used in testing and QA. As you can see, every part of the application development lifecycle is enhanced by container-based architecture. The advantages that you get from development and testing all the way to production deployments make it well worth the time it takes to learn and build and deploy applications using Docker. Microservices is a buzzword that you'll hear a lot about these days. And we're going to talk about it more in this course because Docker makes microservices really easy. Here in this course intro, I want to describe the basics of microservices and some of the scaling advantages that they provide. First off, let's look at the monolithic application, represented here by a gray box with the blue boxes that represent our different modules or components within that application. It's one big application, and it deploys as one piece, and it usually also has one data source as well. A developer will run the entire application when they're developing locally, and the same application grows and changes over time. Many companies will start off with monolithic applications for several reasons. First off, monoliths are easy to develop rapidly, at least at the beginning. They're also simple to deploy, again, initially at the very beginning of a project. They're also less to architect, you simply build features and get things done. But they do have their negatives, and these negatives usually start showing up as a company grows. The application complexity inevitably grows as the application gets larger and larger. Unintentional coupling is also inevitable in a monolith as it grows. Look at all those lines between the modules. While the modules themselves have clear-cut boundaries, in a monolith, it's just too easy to have the coupling go back and forth in all different directions. Also, scaling is very limited in a monolithic application. Microservices, on the other hand, are built and deployed as discrete pieces of the application. Now, the definition of micro varies depending on who you ask. Some people refer to it as a handful of services, and others believe it should be dozens, if not hundreds of services, none larger than a single page of code. Regardless of how small you break it up, microservices generally refers to the breaking up of an application into discrete and separately deployable components. Here's how microservices look when they communicate directly with each other over HTTP protocol. You'll notice that each service manages its own data as well. This makes the coupling much less accidental and much more intentional. It also means that you can and should use different databases that are each suited to the type of data each service is managing. Now, microservices does come with several disadvantages. First off, you're now managing 4 applications instead of one application. There's also some increased latency as multiple applications can't communicate quite as efficiently as a single application can. Here's another way that microservices can communicate with each other, and that's over an asynchronous messaging queue, such as RabbitMQ or Kafka. Here, there's even less coupling, as different services operate asynchronously via publishing and subscribing messages. Now let's look back at that monolith for a second. When it comes to scaling a monolith, you really don't have a lot of options. The two choices you really have are to scale the application to a more powerful machine or horizontally scale it to multiple machines. And then you can also scale the database independent of the application, but that's pretty much where your options run out. Scaling microservices is a much more customizable experience. You can scale each portion of your application independently, adding resources only where they're needed the most. You can also scale parts of your data independently, as each set of data is managed separately. The messaging queue can load balance between multiple subscribers, or if you're using HTTP protocol, a service can have load balancing in front of it. So there's microservices in a nutshell. For those who are new to microservices, the biggest change is not the development process, but in architectural thinking. So if microservices and services are a new concept for you, I encourage you as you go through this course to start to challenge the way you think about application architecture. Try to think about ways to break up your applications into smaller, individually deployable pieces. And as this course will show, Docker makes the deployment part very simple. In this video, we're going to cover the most basic of Docker deployments. First, we're going to set up a production Docker server, and then we're going to build and deploy a simple monolithic application. And it's all going to happen within minutes. Let's start off by creating our Docker server. For this example, I'm going to use DigitalOcean since it's a really fast way to create a virtual private server. I'm logged into my account and I'm going to create a droplet, which is their name for a server. I'm going to use an Ubuntu box, and I'm going to add my SSH key to it. Then I'm also going to give it a name. Okay, in a little less than a minute, I'll have an Ubuntu server running. So once that server gets up, I need to do three things. I need to install Docker on the machine, and then I also need to create a deploy user, since it's a bad security best practice to deploy as the root user. Lastly, I need to do a Docker login so I have access to my private images on Docker Hub. There we go, it's been created, and I can copy this IP address and log in. Now you remember I added my SSH key, so it didn't ask me for a password. Now we can go ahead and install Docker, and that's very simple. You just go to git.docker.com. And you'll notice it's actually a shell script that it gives you. And in comments, it'll show you the commands that you'll run on various machines. You can either run curl or wget. I know that wget is on an Ubuntu box, so I can copy and paste this command. And there you go, Docker's installing, and that'll take a little bit. While that's installing, let's go ahead and look at our working files for this lesson. I have create deploy user sh, and these will be the commands you use to create a deploy user. We're going to create a deploy user, and then we're also going to add that user to the Docker group, so it'll have access to run Docker. Lastly, if you have an authorized key like I did in this scenario that I want to add to my deploy user as well, I'm going to create an SSH folder, add that authorized key over, and I'm going to change the owner of the new file I created to bdeploy. So these are the commands I'm going to run. Let's go ahead and copy our first set and run those on our server. There we go, I've created my deploy user, added it to the Docker group, and now I've changed ownership of that authorized keys file that I made. I can exit, and I can log in as deploy now. Let's go ahead and copy that IP address. That worked. Let's verify that I have access to run Docker by running docker ps. Excellent. I can talk to the Docker engine. Now I just need to do a Docker login. Okay, I'm all set up to now talk to my Docker Hub account and get my private images. And now I can exit out of this and I'm done with the server. The last thing I'm going to do is copy this IP address. I'm going to paste it into my deploy shell script, which we'll get to in just a moment. So now let's go ahead and look at this monolithic server that we're going to be deploying, this monolithic application. It's server.js, and it's not very monolithic at all, but it's simply a single application that we're putting into a single Docker container. So as far as our deployment workflow is concerned, this could be 10,000 lines of code, or it could be just what you see here, a simple Express.js server that says hello world. Let's look at our Docker file. It's very simple. We're going to add our files to app, we're going to expose port 3000, and we're going to run npm install. And then when our container starts up, it's going to run node server.js. You'll also notice I'm using an Alpine node base image up here. The Alpine node image is very lightweight, so it allows my deployment to be extremely lightweight. Most Node.js applications will be just fine with an Alpine node container. Okay, let's go and look at this deploy file, this deploy script that we have. It's going to start off by running docker build and docker push on our deployment machine, which in this case, this is my machine that I'm on right now. This could also be a Jenkins continual integration server, or it could be Circle CI. But these first two commands are going to be happening on the machine that's running the deployment. Then we SSHN as our deploy user to our new machine that we just spun up, and we're going to pull that sample node image that we just pushed. We're going to stop web, we're going to remove web, and then we're also going to remove any images associated with the last version of web. We do this because one of the limitations of Docker, or one of the well-known problems you can run into, is you can have containers that build up and build up and pile up, and images that build up and build up and pile up on your server. And you don't want that to happen. When we stop our web server here, we're also going to remove that container right away. And then we're going to remove images so that only our new images will be used. Then we're also going to tag our latest, which is what we just pulled, as current. So that way we've tagged latest as current, and then we're going to go ahead and run current. And we're going to give it a few flags. One, we're going to give it a restart always flag. That way, if our server for some reason goes down and reboots, then it'll automatically restart our web instance. And we're also naming it web, and we're exposing port 3000 publicly so we can access it. You'll notice a couple things I've added here as well. I've added this true double bar. And what that's going to do is that's going to ignore any errors. Just in case for our first deployment, there won't be a web container to stop and remove. So those would normally throw errors for our first deployment. This way it won't throw errors if there is no web container to start, stop, and remove. So there we go. Our deploy sh is going to run. That's all it takes to run a deployment. All we have to do is change it to an executable. So we do that by writing chmod +x. Now it's an executable file, and we can go ahead and execute it. So there we go. We're building our container on our machine. We're running npm install, and then we're going to push our container to the Docker Hub registry. That happened quickly. It's a lightweight base image, as I said. Now we've SSH'd into our remote machine. We've pulled the new image that we've pushed. We've removed web, or we've tried to, because if you'll notice there's an error right here. We couldn't stop or remove the container web. We also couldn't remove any images associated with it because there was nothing to remove. Oh well, we went ahead and started our new web instance. Let's go ahead and check out and see if that deployment worked. IP address, port 3000. And there you go, we have hello world. Let's go ahead and make some changes to our application and redeploy. Let's go to server.js and change it to hello there. And run that deploy sh one more time. We're going to build our container. It's going to build a little bit faster than before since it doesn't have to do as much as it did. We're pushing it. Now it's SSHing in to our remote machine, pulling the latest. It stopped web, it removed web, it deleted any images we no longer need, and it redeployed my application. Let's go check it out. So as you can see, within a few minutes, we are able to provision a production machine. We are able to package up our application and deploy it to that machine, make some changes, and redeploy it. This is how you deploy a basic monolithic application using Docker. In this video, we're going to cover the local development workflow with Docker. We're going to configure a local Docker container for development so other developers on the team don't have to install anything other than Docker to get up and running with the application. That's right, for this Node.js basic server we're going to use, a developer won't even need to install Node.js. Now it's important to note that the workflow we're going to be learning in this video will not work correctly with the old Docker Toolbox installation. You'll need the newer Docker for Mac or Docker for Windows installed on your machine. Now our example for this video again will be a basic Node.js server. Now, if you're not familiar with Node.js, that's completely fine. What really matters here is that we'll be doing two things. First, we'll be sharing all the files on our machine as a volume within the Docker container in real time. That way, when we save files on our machine, those changes will be reflected and noticed inside of the Docker container file system. Second, we'll be managing all of our external dependencies completely within the Docker environment. In the case of Node.js, these dependencies are NPM modules, and they're defined in package.json. Now, whether you use Node or not, most dependency managers will be pretty similar to this. They will have a file that declares the dependencies required, and then they'll also have an installer that fetches those dependencies and installs them somewhere on the local file system. Okay, let's go to point number one. We're going to start by sharing all of our files into the container. Let's look real quickly at dockerfile.dev. This is the definition of our development environment, and it's pretty much the exact same as our production Docker file. We've only changed two things. One, we're not adding our app files into the container, and we're also not running an entry command. Let's go look back at that dev file again. We're starting from a base image, we're exposing port 3000, setting our working directory, and setting our node n environment variable. Then we're adding one critical file, and that's our external dependencies, our package.json, and running npm install. This is all we need to have a development environment for our application. Let's go ahead and look at our Docker Compose YAML file now. You can see we're defining one service, web. We're building off of the dockerfile.dev, and we're running a command, node server.js. We're also exposing two volumes into this container. We're exposing all of our current files in our current directory into app, right here, and then we're exposing another volume on top of that, which is node modules. You'll notice we're not sharing node modules from our machine. When we define a volume with only one argument, here's what happens. It starts by building our container and running npm install, so we have node modules. On top of that layer, we're going to add all of the files from our system. And then, on top of that layer, we're going to re-add the volume that contains node modules. So that way, when we overwrite node modules, they get overridden yet again. That may sound confusing at first, but it's just a workflow that works very well. As long as you remember the simple rule, expose your working files, and then expose your dependencies on top of that, you'll be good to go. Then we're going to take port 3000 from our Node.js application, and we're going to expose that out as port 80 so we don't have to type in port 3000 every time. That's enough talk. Let's go ahead and run Docker Compose up. So as you can see, it's building our image, and we also get a visual demonstration of those layers stacking up. Our container's built, and it's running on port 3000, and since we're mapping port 3000 to port 80, we can just open up a browser and go to localhost. There we have it. Okay. So let's go ahead and make a change to our file now. We're shouting OK now, and I feel like that's a little bit too aggressive. So let's go to server.js and just change it to OK. Now to reload it currently, I have to cancel Docker Compose and restart Docker Compose. It's not a very efficient workflow, so we're going to improve that in a little bit. Docker Compose has been stopped. Let's restart it. And there we go. That exclamation is gone. So let's go ahead and now make a change. And we want to actually live watch our file system to improve this workflow. And to do so, since we're on a Node.js application, we're going to install NodeMon, which is the standard file system watcher for Node.js applications. And this will actually accomplish two things. First, to install NodeMon, we're actually going to have to add a dependency to our project. And then we're also going to use that dependency NodeMon to watch the file system. So to add a dependency while our container is running, and that's very important for the easiest possible workflow, we can actually execute commands within that container. So I can run docker compose exec in the web container, and now I can run any command inside of that container. So I'm going to run npm install save dev nodemon. You can see that there it's installing the dependency. And now I'm going to be able to go to my package.json file and find that the dependency file has been changed. There you go. NodeMon has just appeared. Now you'll notice I also have this node modules folder. It's empty, but it exists. I call this ghosting, one of the side effects of developing within a Docker container. You'll see the folder, but you won't see any of the dependencies that got installed into that. So this can be solved with a simple git ignore file, that tells us to ignore node modules should it appear. But we're not actually getting any of those node modules that got installed, we're just getting the node modules folder. All that really got changed was our package JSON file. So our project still only consists of these 6 files, which is an excellent workflow. So now I can actually go to my Docker Compose file and change this to use nodemon. And now I can stop and restart Docker Compose. And you can see that that terminal output looks just a little bit different this time. That's because we're actually using nodemon instead. Let's go check. Yep, my server's still running. But now it will real-time watch any file system changes inside of the Docker container. And since I'm sharing these files as a volume within the container, any changes made on my machine will trigger file system changes in the Docker machine. So I'm going to add that exclamation back, and you can see that it restarted the server. So without changing anything, I can get that exclamation. So now we have an incredibly fast workflow. I can add 3 exclamations, and they're there. Docker container that's running as if I was on my own machine, and it only writes the files that I really want it to write to my machine, which is my source files and my package JSON file. So that's local development within a Docker container. In this video, we're going to wire in a database to our local development workflow with Docker. That way we have a complete ecosystem on our own machine, and we don't even need an internet connection to do development on our project. So let's go ahead and look at the web server folder in our working files folder, and let's look at that Docker Compose YAML file. You'll notice we've gone from 1 service to 4 services. We still have our web, and we've only changed one thing. We've added depends on. That way, whenever we want to start our web service, it's automatically going to start the MySQL service alongside of it, since it needs it. And then we've added our MySQL image as well. Now, we've pretty much just gone with a basic MySQL image, and we've added some environment variables to set up a basic database for us. And I've just made all the values test. Since it's just going to be running locally, it really doesn't matter. And then I'm exposing port 3306 out, so that way I can actually use a visual editor to look at this MySQL database and inspect it on my machine. Okay, let's go ahead and run Docker Compose up now. I'm in the web server folder of our working files, since that's where the Docker Compose YAML is, and I can run Docker Compose up. So it's creating the web server, and it's also creating the MySQL server. And it's taking just a little bit longer this first time since it has to create the user and the production database. There we go, MySQL's running, so now I can connect to it, and I'll use a GUI editor so you can actually see that the database is running. If we want to work on it locally, connecting with a visual editor is extremely easy since it's just running on localhost. And it'll ask me to change that to 127.001, which is fine, and then test, test, test. And there we go, we have an empty database. I could go ahead and easily make any schema changes here, but we don't want to do that since we don't want each new developer on the team to have to build out a local database manually. So we're going to want to put the schema into code for them to use migrations and fixtures. Now it's important to note that it doesn't really matter which database management tools you use since there are so many good ones out there. I've chosen Connects.js since this is a Node.js application to manage the fixtures and the migrations. The most important one is the migrations, and I gave you the code for both of these in case you want to see how I did it. The migrations are important because these will also be used to manage the production database schema. That way, our local database schema will always identically match the production database schema. Now we can also take this migrations code and we can put it into a GitHub repository and add continuous deployment to that. So when we make any changes to the migrations code, it automatically gets deployed to staging or production just as we would in application. And the fixtures are the actual test data that they'll use locally on their local environment. So the fixtures are something the developers will run locally, but they don't ever really make it into production. So let's go over to our Docker Compose YAML, and we're going to uncomment these that were commented out. I have these 2 commented out because we don't want to run them every time when we're developing our application. They really only need to be run the first time, and then migrations needs to be rerun if we ever change our migrations or our schema setup. So I'm uncommenting these and I'm saving my Docker Compose YAML, and now I can go to this other terminal window. Now while MySQL is running, that's very important that MySQL is running over there on the other side, I can now run migrations against it with Docker Compose run. And I'll remove the container when it's done because I don't need to keep it around. There we go, migrations ran. And since it's depending on MySQL, it can easily make a MySQL connection. It's a part of the same Docker Compose file. And you can see that it ran one migration, this users.js file. So I should have a users table now. If I go back and I refresh, I actually have three tables. I have the connects migrations table, which showed the migrations that have taken place. And then I can also have the users table, which is completely empty. So I'm a local developer. I need some test data. Let's also run fixtures. And now it ran fixtures. If I refresh again, I have Jack, John, and Bobby as users. Excellent. So now I can actually go back to my program code and I can tell it to pull in those users. I have these pre-set up in the code, so I can just comment them out. And let's get rid of res send OK. Instead of saying OK, we're going to fetch the users and then send that data back over the wire. Let's save this. NodeMon restarted my server, and now I can go to localhost. And there we have Jack, John, and Bobby. I can also go to that database real time. Let's change Jack's name to Jim. And my changes are reflected. So that's how you do a local database workflow in Docker. It's really about the same as you do with any other database. What makes Docker great is it's extremely easy to run that local database because you just run a container. And then you can run all the provisioning against that container very easily as well. In this video, we're going to create our production database. Then we're going to run all of our migrations against it so the schema is correct. Lastly, we're going to connect our web server to that database and we should be good to go. Let's begin by SSHing into our production server from lesson 201. I have that IP address, which is already stored in my deploy script. Right now our web server is running if I run docker ps, but I won't be able to connect a database container to it if we run it. In order for our containers to communicate with each other, we have to create a Docker network and add all of our containers onto that network. Let's prove this by running an Ubuntu container and telling it to ping the web container. You can see that we have an unknown host. So what we need to do is create a network. We do that by simply running docker network create. And I'm going to call this network app. Let's go ahead and change our deploy script to run the web container on the app network and redeploy it. So all we need to do is add net app. Excellent. Exit out of our server and rerun that. So it's building the container, pushing the container, pulling the container, and rerunning it. The only difference will be is that it's now running it on the app network. Okay, let's SSH back into that node. Now let's run that exact command again, except for this time we're going to run it on the app network. Check it out. We're now able to successfully ping our web app just by calling it web. Docker networking makes this really simple. Now let's go ahead and run our MySQL container on the app network as well. It's quite a long command, so I'm going to copy it from off screen and simply explain it to you. We're doing docker run. I'll clean this up a little bit. There we go, that's a little cleaner. So docker run, our net is app, our name is MySQL, and then here's those environment variables that we had to set before, except for I changed everything from test to production. It's not secure, but I'm going to destroy this as soon as we're done, so it'll be totally fine. So production is our password, production is our database, production is our user. I've set the restart policy to always. I'm running in background mode, and then I'm using MySQL 5.5. Let's go ahead and run it. It looks like that worked. Let's go ahead and try to connect a MySQL CLI to this and see if it works. Let's go docker run. Our net is app. And let's just run a prompt. Let's go ahead and connect to MySQL. And let's see what databases we have. Excellent. Let's use production and see if any tables exist, which we know they won't. So let's go ahead and open up another tab and let's run our migrations. I've got another tab going, and let's SSH back into that server in our other tab. And we're going to go ahead and run those migrations that we ran before. Docker run, same net of app. That's going to be very important from now on. And then we're going to run will r stern testdb migrations, which is the migration image that we built from that repository. There it goes, and it looks like it successfully ran. Let's go ahead and show our tables again. Hey, we now have a users table. Excellent, so our migrations were a success. Let's just go ahead and run a redeploy on our web app. That way it'll pick up on that new database connection. Let's refresh our application. We now have an empty array of users because we haven't added any fixture data, which is of course what we want to do because we don't want to put mock data on our production servers. We only want it to be real production data. All right, the only thing that remains is we want to add a deploy script for our migrations now. And as you'll see, the deploy shell script will look almost identical to what we have for our web server. We're going to build and push this container, testdb migrations, and then we're going to log into that server and we're going to run it against the MySQL database, which is just including net of web. And our configuration, as you can see right here, is whenever we're on production, we're going to use MySQL and all the passwords will be production. Again, not secure, but works excellent for this example. So there you have it. We've deployed our MySQL database. It's running in the wild. We can real-time run migrations against it at any point, and we can also redeploy our web server completely independently. Hey, would you check it out? We've got our first entry in our production database. Apparently a user has signed up, which means we can go to the front end of our app, and we can also see his name in the listing. This is excellent news, but it also means that we're now at the point where we need to manage backups and restorations of production data. So that's what we're going to cover in this video. We're going to show you how to keep your prized, precious data safe and sound in case something should ever happen. So let's start off by opening a new terminal over here and SSHing into our server again. We're going to open up another MySQL client for the first method and take a MySQL dump of all the database contents. This is the fastest and simplest way to take a database backup. I'm going to leave this client open over here because I'm going to cause some mischief in a few minutes. But for now, let's go ahead and create a new Docker container that can connect to our MySQL database. Let's run docker run on our net of app. And then we're also going to remove this whenever we're done with it. Let's run a MySQL 5.5 environment. And then inside of that, we're going to run MySQL dump command. So now let's connect to that MySQL server that's running. So we've connected to MySQL with a username and a password of production, and we're going to take a backup of the production database. That is a lot of words production. I probably should have thought through some of those words when I was creating my first settings. Now we want to save this. For now, we'll just save it to this Ubuntu machine that's running the whole website. While this is not the best example of where to save your backup files, because after all, what happens if your server has an issue, it'll work for right now. So if I were to list files, you can see that I've got a production SQL that I've stored to the server itself. Now let's say something goes wrong over here. Let's say someone is deleting from a user. Oh no, and they forgot to put in a where clause, so we just lost all of our users. There you go, select from users shows that nothing is there. Let's go ahead and restore that MySQL dump in almost exactly the same fashion that we created it. We're going to docker run again. But instead of doing MySQL dump, we're going to MySQL and we're going to pipe the information in from the file, which means we have to add one very important flag, and that's the I flag, which means we're going to pipe in some content. All right, now let's go ahead and run MySQL. And let's pipe in that information. There's our backup. That's going to run. And let's check our users. Oh, good. Our users have been restored. So method number one is going to take a MySQL dump, store that file somewhere, and then rerun that file in case you lose that information. But we really don't want to store the file on our machine, so I'm going to remove that. And then we really don't want to have to run this by SSHing into the machine either, so I'm going to exit out. We can run this exact command over SSH, which means that it can be run from anywhere. You can see this is essentially the same command. The only difference is, first I'm SSHing in to the server, and then I'm running that command. Now if I were to list files, I've got production SQL on my local machine. So then, again, let's say somebody causes some mischief and deletes those users again. We can run that production restore straight off of any machine. So there we go. It's that exact same restore command. We're SSHing in, we're running with that I flag because that's very important, and then we're connecting to MySQL, we're sending the MySQL file over, and our users are all back. So there are many ways that you can back up data in Docker in production. The simplest way, like I showed here, is to just connect to your database and work with it specifically on its backup and its restoration protocols. Another more generic way is to actually back up the data volume for the entire container. Let's go ahead and SSH in again and let's look at some things. Okay, so let's go ahead and do a Docker inspect in the MySQL container. If we scroll up, we'll eventually see that we're sharing volumes. Here we are, var lib MySQL. This is the volume that's being shared of all the MySQL data. So we can actually run another container, connect to the volumes from the MySQL container, and back up those directories. Let's go ahead and do that. So this is a very similar way, but it's also very different in that we're not running a directory store of MySQL's interpretation of the data. We're just running a backup of the data itself, the complete raw folders that are sitting on the file system. So go Docker run, and then we're just going to log into a generic Ubuntu bash prompt. What's very important here is that we pull our volumes from MySQL. There we go, volumes from MySQL, and then bin bash. So now if I were to list var lib MySQL, you can see that I now have access to all the MySQL data. So I can simply do a tar backup of this. There you are. Let me list this. And I have backup.tar. That's a backup of all my MySQL information. Again, let's say somebody's causing some problems. Delete from users. If I select from users, they're gone. Oh no, that's a problem. So let's go ahead and restore this information now. Come back over here, and we will now restore this. So that's restored. Of course, you'll notice the users aren't restored yet. Since it's in the file system, I actually have to reboot my container. Docker restart MySQL. And now within moments, my information is back. I'll just refresh it in here so I don't have to reload that entire MySQL CLI again. So that's another method. You can connect to a volume and you can back up and restore those volumes directly. Or you could take those volumes and restore them to a completely new MySQL container running in a completely new data center. There's a lot of options when you're actually working with volumes. Let's exit out back to our machine. And you can run that backup, that tarball backup from your machine as well, exactly as you would. Now, it can be slower, I do have to warn you, since there's a lot more going on than simply taking MySQL information and exporting it out. You can notice it's going much slower here. So if you have a very large database, this method probably will not work for you. But I'll give you the commands to back up and restore from a remote location. There's one more option that you can use, and that's that you can look for images that have been created by other people that will do more customized backups for you. Here's a great one that I'll show you, and that's from Tudum Cloud, who has actually been acquired by Docker. Now it's called Docker Cloud, and it's called DocUp. This will connect to a MySQL database and run a cron job backing it up to AWS S3. You'll include your AWS account token information and your S3 bucket name, and it'll automatically take backups automated on a cron job if you want to AWS S3. And you can also run it in restore mode where it will restore from AWS S3. So there's a lot of options when it comes to backing up Docker information. And as you can see, it's not so much how can you do it, it's more of how do you want to do it. In this video, we're going to examine testing within our Docker environment. And once testing is in place, we're going to set up continuous testing using Circle CI. Let's begin by getting tests up and running for our local development environment. To keep things simple, we'll keep using the sample node app that we've been using. But it's important to mention that no matter what you're using, the process really doesn't change from what we're doing here. The command just changes. In the case of a Node.js app, the standard test is npm test, which runs the test script in the package.json file. You can see one was automatically made here when we did our npm init a while ago. It echoes error, no test specified, and exits code 1, which is an error. We're just going to change this to code 0 and pretend that our test command passed. Now, normally in a Node.js app, this would probably be something like Mocha, which will exit with a code 1 or a code 0, depending on whether tests pass or fail. But for the sake of this video, we're going to manually set it to 0 for passing or 1 for failing. So there we go, our tests are passing now, and the developers can now run npm test, and there are no errors. Of course, we don't want the developers to actually run npm test, because this would require them to install Node.js and npm on their machine. Instead, we're going to go ahead and have them run that within the Docker container. To do that, we simply build the container and then run npm test within the container. So let's go ahead and build that container. I'm going to steal that build command from my deploy shell script to make it easy. Docker build, tag it will stern sample node, and we're building from our current directory. And you notice that built really fast. That's primarily because in our Docker file, we're first adding our dependency file, package.json, then running npm install, and then adding the rest of our application over. So as we have to do rebuilds and rebuilds, that'll happen very quickly. Again, it's very important to take the little bit of effort it takes to tune your Docker file because it's going to save you a lot of time in the long run. Okay, now all we have to do is run that container and run npm test within it. I'm going to run it. I'm going to remove it when I'm done because I don't want that container hanging around. And then I'm just going to simply run npm test within it. There we go. Our tests, quote unquote, passed, and everything is good to go. Let's go ahead and change these to failing now. Our tests will now fail, and we can run that exact same command. Actually, we can't run that exact same command because we do have to rebuild our container. So I'm now going to change this command to be slightly longer. I'm going to concatenate the two of them together. We're going to build it, and then we're going to run npm test inside of it. Unfortunately, when we changed our package.json, you notice it has to do an npm install again. This will not usually be the case because we won't usually be hacking in a fail or a pass in our package.json. Package.json only has to be updated when our dependencies change, which it does happen often, but it doesn't happen nearly as often as code changes. So there we go, it worked. We're now failing our tests and we have an error. Okay, let's change that back to passing. We're all set up to go. Let's get Circle CI now running this on GitHub. So let's go to our GitHub repository. You can see there's our GitHub repository for this project. Let's go to Settings, Webhooks and Services, and let's browse the integrations directory and add Circle CI. Oh great, it's already been added because I've already given Circle CI access to my GitHub account. Now all we have to do is go to circleci.com. Let's go ahead and log in and add a repository. You can see once you've given Circle CI access, it automatically has access to all your projects. So let's go ahead and build this sample node Circle CI project. And there you go, it's already building. Now, it's actually going to build wrong because it's going to, out of the box, notice package.json and think that it's a Node.js project. So we're going to actually want to change that and override the default behavior and have it run within Docker. We do this by adding a Circle YAML file. And you'll notice the configuration is going to be very simple on this. We simply have to make sure Docker is on our machine, and then everything else will work. Because again, all we need is Docker, and then the rest of the environment configuration happens within that Docker file. So let's go Machine Services and add Docker. And let's go ahead and make sure that our container is built as a dependency to our project. There we go. So we're going to build our container before we try to run our tests. And now let's run our tests. There we have it. We've added a Circle YAML. Let's go ahead and save and commit our test to GitHub and see what happens. We've pushed it to GitHub. And let's go over to our Circle CI build now. You'll notice there's a few builds already in here. That's because I was messing around with this sample project a while back, and it all kept up with me. But here's my current build that's running. You can see, added Circle YAML. Here it's starting our Docker service for us. It's restoring a cache from our prior builds,
and then it's going to build our machine and run our tests. About the only thing you'll notice here is that builds take just a little bit longer because it has to run npm install every time. And this is actually a good thing because we always want our test environment to be pristine. We want it to be exactly what's going to be happening with the code that we deploy. Excellent, our container's been built. It's running npm test within our container, and it's green. Let's inspect it. It passed. It's wrapping up, and our test is complete. We have a green check mark on our build. Let's go ahead back to our repository and create a pull request and watch it build our pull request as well. I'm making a failing branch. Let's go ahead and make this test now fail. There we go. I've made a branch called failing branch. I've changed my exit code to 1 so the test will fail, and I've pushed it up. Let's go create a pull request now. And you'll notice that Circle CI is running tests against this. We can go ahead and watch this test if we want to, and watch it go through all the steps that we just had it go through. Just in the time it took me to get through that pull request, which I'll admit I stumbled through it a little bit because I'm not used to doing it with my mouse, it almost built the container already, so our tests will be done very shortly. There we go. Our tests have failed. We know that this pull request is not safe to merge. So within just a few minutes, thanks to Docker and its complete containerized environment, we've been able to get continuous testing up and going. Once we have continuous testing in place for a project, it becomes very simple to move one step further into continuous deployment. For those of you who haven't tried continuous deployment yet, the concept is simple. Production servers should always be running code from the master branch in your Git repository. For those who are used to manually pushing a button to deploy code, the perceived loss of control with continuous deployment can be scary at first, but almost everybody who makes the shift never really wants to go back. And there's a few reasons for this. 1, the code on the master branch is easily reverted and rolled back, which makes rollbacks as simple as ever. Master being equal to production also alleviates miscommunication between team members as to which code is currently running in production. Also, if your project is deployed in large releases, your pull requests can be merged to a different develop branch, which periodically merges into the master branch to trigger production deployments. So the workflow still works if you do large releases. So let's go back to our Circle CI and let's go ahead and make some modifications to allow continuous deployment to take place. We're going to need 2 things. We're going to need to be able to log into Docker Hub so we can push our built image, and we're also going to be able to need to SSH into our production server so we can tell it to pull that image and redeploy. Essentially, we need to be able to run our deploy sh script that we've been using. So we need to be able to push, and we need to be able to deploy to that server. Let's go back to Circle CI and add some variables so we can do this in a secure way. We're going to start off by going to environment variables. We're going to add the Docker email, the Docker user, and the Docker password. Circle CI will store these values securely for us and then export them into environment variables so our script can make use of them without them having to live in the code. I'm going to add them now off screen so you don't see my credentials. There we go. I've added my Docker email, my Docker user, and my Docker password. Now let's go on to SSH permissions. We need to add the SSH key that allows us to SSH into that remote machine and make a deployment. Again, I'll add this off screen. There we go. I've added the SSH key for our server, which I got that IP address from our deploy script. There you can see the .59 server. And then I've added in my SSH key that got added by DigitalOcean when I created that server. All right, so Circle CI has everything it needs. Let's go back to our Circle YAML script and add a simple change. We simply need to add a deployment command, which will fire if the tests are ever successful. Under deployment, you can create as many different variables as you want, and you can name them whatever you want. So we're going to name our first one production, and production will trigger whenever the branch is master. And then you get the option to simply run any commands you want. So we're going to log in with Docker, and we're going to run our deploy shell script. So there we go, we've logged into Docker. we're going to run our deploy shell script. Then we only have one change to make to that. We don't want to have to rebuild our container again, because if you'll notice, we're always building our container before we run our tests. So we don't have to rebuild that again. We can simply push it, SSH into our server, and run our deploy script as usual. Let's commit these changes to master and see what happens. It's pushed up to the master branch. Let's go watch Circle CI and see if that deployment is successful. Let's go ahead and speed this up so you don't have to watch the whole thing. There we go. Our test was complete. Let's go ahead and look at this deploy sh command. You can see that it logged into the remote server. It actually first pushed our package, then it logged into the remote server, pulled all the layers, and ran through with no issues. So now our deployment should work. Let's go ahead and grab our IP address and check out our server. Make sure everything worked successfully. And there you go, it still works. Let's test this out again by making a simple change to our app and redeploying. Instead of getting the users and sending, we'll just res send OK. And now we have another build running, and again, we'll speed this up for you so you don't have to watch the whole thing. There you go. Our tests have passed successfully. It built our container, tested it. When the test passed, it went ahead and pushed the container and triggered the redeploy script. Let's check out our website. And our response is OK. So there you go. That's how you set up continuous deployment with a Docker workflow. We have our Node.js Docker application using continuous testing and continuous deployment. The only thing we want to do to wrap up our whole deployment workflow is add a few more environments. So in this video, we're going to add a staging and a QA environment that we can automatically continuously deploy to based off of a staging and a QA branch in GitHub. And they'll do essentially the same thing. When we merge to master, that code will test and deploy to production. When we merge to a staging branch, or force any branch we're on to overwrite staging, then it will automatically deploy the staging branch to a staging server. So I've gone back to DigitalOcean and I've spun up two more servers, Docker QA and Docker Staging. And then I've gone through the setup procedure. I've added Docker and I've added a Docker deploy user. And then I've also grabbed their SSH keys and I've added those to Circle CI. So now Circle CI can automatically connect to these two nodes and run a deploy script against them. So now all we need to do is a couple things. First of all, we're going to change our Node.js application a little bit to make it more multi-environment friendly. Let's begin by looking at this config.js file here. As you'll notice, it's kind of all manually configured based off of environment. If it's production, we're going to use these credentials for our database. And if it's our development, we're going to use these credentials. What I don't like is that code is actually switching the credentials based off of environment. It's a lot safer to actually have the code be exactly the same, and it automatically configures itself for each environment. We're going to take these values and put them in environment variables in the Docker file. We can really do it in two places. We can add them in the Docker file if we're 100% certain that we are going to be pushing private images to a repository, which is Docker Hub, where no one else will have access. If we're not certain that no one else will have access, we really shouldn't put them in the Docker file because that will be visible to anyone who has access to our image. If we don't want to put the environment variables in the Docker file, we can also put them in the deploy shell script and run them in the run command with the E flag. But for this case, it's a lot cleaner and a lot simpler to put them in Docker file when you can. So instead of storing them here, we're going to store them in process environment variables and we'll access them that way. So in Node, that's process.env. We'll call it dbname and we'll call this host. I'm just going to go ahead and snatch that there to make it easy. And db password. There we go. So that is the exact same snippet of code across all environments. Now we can put those environment variables in our Docker file, and we can actually build the image we need for each environment. Let's go back to this production Docker file now, and let's add a few more environment variables.
And if you'll remember, it's always production. Production, production, production. Not the most secure credentials in the world, but it's what I'm using for this example. There we go. I can save that to my Docker file. I'm also going to copy and paste those. I'm going to go back into my local development. And these were all test, test, test. There we go. So now I can also save my Docker file and call it dockerfile.staging. So this will be my staging build, and I can change all these to staging. Everything else remains exactly the same because we really do want to build the exact same code, the exact same image across all environments. We just want it to be configured differently since it's going to be connecting to different databases. So there we go. And then I'll also make a QA version. And there's our QA version. Excellent. So now let's go ahead and make similar tweaks across our deploy shell script. We're going to make a staging and a QA version of this as well, since after all, we're deploying to a different server. So I'm going to save it as deploy staging, copy that IP address for staging. There we are. And I accidentally didn't put a period in there. This will be staging.sh. There we go. And let's go ahead and also save the next one as QA. And copy the QA IP address and paste that in there. Then we're going to make one other very critical change. We do not want to push staging and QA builds with the latest tag. That will overwrite and mess with our production builds. Because if we push a staging build to the latest tag and production happens to do a deployment at the same time, production will pull our staging code. Not a good move. So we want to make sure that on staging, we are pulling the staging tag and we are running the staging tag. We can still retag it to current on our machine as we're doing here, since this is just our staging machine. And then again, we also want to push the staging tag, not the production tag. So there we go. Let's make that same change to QA. We're going to push QA and we're going to pull QA. Tag QA as current and run current. There we go. Our scripts are in place. The only thing we need to do now is change the permissions on those scripts to be executables. There we go. They're both executables. So now all we have to do is go to Circle CI and tell it to do some different builds and different deployments depending on which branch we're on. And that will change our extremely simple Circle YAML to be a little bit more complicated, but we're going to have it do essentially triple the work. So it's really going to be clean for what it's doing as well. All we need to do is we need to override this build because we want to build based off of a different Docker file for each environment. And then we also want to deploy with a different deploy shell script depending on the branch that we're on. So let's start up here with a dependency. We want to view which branch we're on and then choose our Docker file accordingly. Luckily, Circle CI sets a great environment variable for us, circle branch. So I can do if circle branch equals staging. Then we're going to run our command. So that's simple enough. And then we can also do the exact same thing for QA. We're going to build our container again. And the only thing we want to change here is we want to specify the file. We want to choose Dockerfile staging. And then I'll also do the same thing here, Dockerfile QA. So if our branch is staging, we're going to build off of Dockerfile staging. If our branch is QA, we're going to build off of Dockerfile QA. Excellent. And then the only thing we want to do is we still want to build that master for every other branch. So if we're on a pull request branch, we're going to build the production container. If we're on the master branch, we're going to build the production container. So that'll be pretty simple as well. We just make sure that we're not staging and production. If we're not QA, and if we're not staging. Then we're just going to do a Docker build. I'll remove our Docker file dependency there, which means it'll just use the production standard Docker file, which is Dockerfile. So there we go. For staging, we'll use Dockerfile staging, QA, Dockerfile QA. For everything else, we're just going to use the Docker file. We're going to run npm test just the same. And you'll notice we didn't tag our images yet. That really simplifies our testing portion, and that we only built an image called sample node. So no matter which branch we're on, it's going to be called sample node for right now. We can test against it, and then we'll handle that here when we deploy. So let's go ahead and copy production to staging. So if we're on our staging branch, we'll run deploy staging.sh. And we also want to do one more thing. We want to retag that latest to staging before we push it, because after all, we do not want to push anything else. So I basically can snatch this tag command that I'm using right here. Let's go back to our circle YAML, and I'm going to tag that latest as staging. So we've built latest up here. We're tagging latest as staging, and then we're going to run our staging deploy script, which will push out staging. That tagging really just allowed this testing portion to be a lot simpler, so we didn't have to do our if like we did. So let's go ahead and copy and paste this for QA, and we're good to go. There we are. We've got our continual deployment going for production, staging, and QA. Let's test it out. I've pushed to my staging branch, and now Circle CI will start a build. Let's verify that that build started, and then I'm going to come back to the terminal real quick. There we are. There's a build in progress. It's running off of the staging environment. So while that's running, I want to show you how you would push to staging from any other branch you're on. Let's say you're on a branch, some feature, and you really like your code and you want to push this to staging. You simply use the push force command. Origin, the branch you're on now, and then we're always going to push that to staging. So I'm working on this branch, I've made some commits, maybe I have a pull request going on, and I want to push this code to staging to get a look at it. I run this command, it pushes my current branch over to staging, the staging build starts running, and my branch is pretty much untouched. I could do the exact same thing for QA. There you go, I've pushed out to the QA branch, which doesn't exist yet, and now Circle CI will also start another branch based off of QA. You can see that that's running as well. Let's go ahead and check out our staging build. It's running. Oh, looks like we've gotten to the deploy phase. Great. We're going to get to look at our code in staging in just a moment. And there we go. Our deployment was correct. You can see that it ran deploy staging shell script. You can see that it built. Let's go ahead and look at our build tests. The staging built. QA did not build. And production did not build. Let's go ahead and grab our droplet IP address. Check out our app running on port 3000. Excellent. My app is working, and as you can see, in just a few minutes, we've gotten continuous deployment going on multiple other environments. If we needed 5 or 6 environments, it really wouldn't be much more work to get continuous deployment running on all of them. Before getting into the rest of the course, I want to take a minute to talk about some of the whys and hows of services and microservices. I'm doing this because if you're going to use Docker already, the infrastructure that you'll create will allow you to seamlessly integrate these concepts in ways that would be much more difficult to do without Docker. Also, the longer I program, the more I see the value of the abstractions of service and microservice patterns even on small projects and working with small teams. We're going to get into some detail on the major benefits of building your applications this way, but first, let's look at some of the weaknesses of monolithic applications. First off, as monolith grows, team members can no longer see the whole picture, or at least it becomes more difficult to see the whole picture. I've run into this time and time again at companies with all levels of developers. No matter how good the team is, there will always be team members who don't understand the fullness of the application or the business as well as others do. As that application or business grows, the difficulty for every developer to understand every component continues to grow with it. This means that it's easier for developers to break things unintentionally. Onboarding new developers also becomes more difficult, and you have to implement more intense testing with more complete code coverage to account for the human errors that are now more likely. The next weakness is that unnecessary interdependencies are inevitable. Even the most finely crafted architectures tend towards interdependency in a monolith.
The pain of code coupling is often harder to notice as well until it's too late, until the application has grown to a complexity level that exposes things that you didn't know were there at first. One of the things that I personally dislike with monoliths is that deployments get scary. You either do large releases with multiple features that can result in more frequent rollbacks and long bug fix cycles, or you opt for continuous deployment, which is nicknamed continuous downtime because it can introduce unnecessary errors or unknown errors, but it can also result in long, slow build times for every single feature. Now, this isn't the case 100% of the time, but again, it's a place this pattern will always tend to gravitate to. Let's take a look at a visual example here. Here's a few Lego creations that I found in my son's room the other day. Clearly, he too was exploring various architectural design patterns, as we can see. The one on the left would represent the monolithic pattern, and the one to the right would represent microservices. Although I would imagine for the complexity on the left to be fully replicated, we'd probably have a dozen or more services on the right, but for now we have 3 in this picture. Now imagine we're going to add 10 new features and we have a team of 5 developers. On the left, we would have 5 developers working on the whole thing all the time, possibly breaking each other's work as pieces were moved around to support the new features. On the right, each piece would just have 1 or 2 developers working on it, and there's also a lot less to break. On the left, we'd probably be better off with periodic large-scale releases. Build times would also likely take longer. And on the right, as each feature was ready, the individual car could just simply ship out right away. It would test and build extremely fast as well, because there just wasn't a lot to each service. Now imagine that the business experienced a compliance issue, and all of the blue pieces had to be replaced with light blue pieces. Can I get an amen from any developers working in the government or healthcare sectors? But anyway, as you can see, it would be a much less daunting process to replace blues across all the microservices, even if the amount of blue pieces were the same as in the monolithic application. It would be a lot easier to tackle and a lot less terrifying to deploy. Lots of cars would never even have to be touched as well, because they would have nothing to do with blue pieces. They just keep happily running as you updated the compliance on the other cars. While this is a simple example, it's actually incredibly close to real life and how it feels to be working in both styles of architecture. So another weakness is that all of your technical debt is in one application. This makes the pain of enhancements and technology stack changes very painful and expensive, kind of as I referenced in the compliance example. Many companies will find themselves with very outdated technology because they're stuck in a monolithic solution that would simply be too costly to change when it's good enough. Frameworks are also painful to change, and often updates are not even made because the pain would be too great. Let's put it this way. Imagine you had 100 small $1,000 loans versus having one large $100,000 loan. At the end of the day, you're in an equal amount of debt either way, but it's much easier to pay off a $1,000 single loan and make a technical pivot in one area of your app than instead of having to pay off an entire $100,000 loan just to make a framework change. That's kind of the difference between services and microservices. There's technical debt involved either way, and the lump of the technical debt might equate to the same, but it's in small batches instead of one large lump. Lastly, there's limited fault isolation with a monolith. A memory leak, for example, in a monolithic application would result in downtime for the entire application. Whereas with microservices, and let's say you had an e-commerce application, and the recommended product service goes down due to a memory leak, the rest of the storefront can still be online and receiving orders. It would fail gracefully. It simply wouldn't show recommended products for the hour or the several hours that service was down. Whereas with a monolith, that same memory leak would take down the entire storefront for an indefinite amount of time. Now let's look at some of the strengths that microservices brings that can complement these weaknesses. First of all, one of the most important things to point out about microservices are that small and simple things are hard to break. Whether the code is object-oriented, functional, event-driven, or any other programming paradigm, we've learned that smaller, simpler functions are more stable and easier to debug and test. And the same thing goes for services. The smaller and less complex a service is, the more stable it becomes. Just like the smaller a function is, the more stable that function is. There's simply less to break. And when it comes to debugging and testing, the same principle applies. Smaller services are easier to troubleshoot, easier to test, and prove that they're functioning correctly and as intended. Let's look back at those 2 Lego creations again. The ones on the right could stand up to a hammer much better than the one on the left. Now, should the hammer win the fight, the right ones will be a lot easier to put back together correctly. Or in an example that's a little more congruent with coding, if I have to upgrade all of the tires, I'd be much less likely to make a mistake on the right ones, even if I was new to the project. There's 2 tires to deal with, maybe 4. Again, there will probably be several apps as well that don't even need a tire upgrade at all. If we've established that smaller tends to be better, which size is the right size? Now, there's really no simple right answer to this, and there's even disagreement among the community and microservices. For this reason, I tend to refer to the pattern as, quote, services and microservices, because not everybody believes that a microservice has to be super small. There are very respected developers that say services should be no longer than 1 page of code, and you should have dozens, if not hundreds of them. And they should have no tests at all because the code that simple and small doesn't need testing. Others believe in services that act like small applications, just broken up pieces of your larger scale application. The true answer to the size question is it really depends. Here are some questions, though, that can help you decide what is best for you and the application that you're working on. First of all, how big is your team? If there are many developers on your team, then that's kind of an easy answer. You'll save a lot of headache if teams can develop, deploy, and test their services independently. 100 developers in one application is generally a recipe for frustration. Now, if you have a small number of developers on your team, say 2 to 5, then the pressure to have a large quantity of services isn't as present. It's more of a question of how many services does our application deserve, which is kind of the premise of question number 2. What's your application like? What are the distinct different pieces of data and logic in your application? What data absolutely must remain in the same database together? Similarly, what logic cannot live on its own but must live side by side? Can some or all parts of the application be asynchronous? Do these parts even have to be considered a part of the core application? Or are they really their own project, their own application? Answering these questions, especially the data question, will likely give you an answer to what your services should be. What size will also lower the complexity and increase application stability the most? For some companies, having 100 services would drastically simplify the overall complexity. For others, it would drastically increase the complexity. And it's also important to remember that service size is not a lifetime commitment. Many companies start with a few services and break them up further as their perspective of the application changes. Okay, so let's get back to the topic, why services and microservices can work so well. When a service is simple and small, and maybe even has its own data, it's really easy to reliably set up performance testing against it and guesstimate the load that it can handle. It's also easier to identify bottlenecks and tune performance because there isn't nearly as much going on in each service. Also, should we discover that hardware is the bottleneck for a service, scaling a service is much more simple, and you're able to scale just the components that need it by scaling those services individually, which can result in a lot of savings in hardware costs because we don't have to scale the entire application just to give more power to one piece of it. Services also have the potential for a lot longer lifespan. This is for several reasons. Not every service needs a public entry point, so security isn't as critical on every single piece of the application. Also, simple components can often last untouched for years on end. If you think of the Linux Unix grep command, it was developed in 1974 but is still used today because it does one thing and does it very well. I've seen the same thing happen with services. Many services are built once, deployed, and barely maintained or touched, often for years at a time. Let's balance out all of this promise and hype that I've been giving you with a few weaknesses, just so you know that I'm being honest with what I'm telling you. While I wholly believe that microservices are well worth the effort and should be the standard default architecture for applications, there are certainly some weaknesses and pain points to be aware of. First of all, DevOps skills are to some degree nice to have with monoliths, but they are a must-have for microservices. You simply don't want to be doing hacky deployments for 10, 20, or 100 services. Things will break. You want smooth, consistent deployments that require minimum developer effort. But to be honest, my experience has shown that hours spent on DevOps pretty much always pays off in the long run anyway, regardless of your application architecture. But that being said, you still do need more DevOps skills for microservices. If you don't fully recover those DevOps hours in deployment time, you'll almost certainly recover those hours in time fixing problems with human error that would be involved in those manual deployments and tasks that you were doing before DevOps. One of the biggest weaknesses that microservices comes into is orchestration. Orchestration is involved and it can be complex in some situations. With monoliths, there really isn't much more orchestration than making sure that there's no downtime as you're deploying to multiple servers. But when you have multiple services, and services depend on other services, which can depend on other services, it can be very complex to deploy all of that out. I emphasize can because the longer you code in microservices, the better you get at decoupling things to really avoid a lot of that pain. Which brings me to my next point. You're forced to think more and build better software. Most developers who begin with microservices engage on a process of realizing that they couple their applications much more than they thought they did. When a service doesn't even have access to some pieces of data because they belong to a different service altogether, it exposes any unintentional coupling pretty quickly, which is really a part of our next point, that architecture costs you more of your time. However, one could argue that this is time you should have been spending on architecture to begin with. So I'll put this down as a partial weakness. You should spend time on every application, thinking through which pieces of code own which pieces of data, and how those pieces of code will interface with each other in a way that requires the minimum amount of data passed in between them. A microservices done well kind of forces you into this thinking. If you find yourself always wanting to connect multiple services to the same database, then you very well might be building a poor design into your application. So especially starting out on a new project, microservices will always make you think more, which can definitely be viewed as a weakness in scenarios with a lot of speed to market pressure, which is why I have it on the weaknesses page. The last point is that testing is very different and can be more difficult with microservices. Again, it doesn't have to be more difficult in that the more you use this pattern, the better you understand it. But at first, at least, testing is generally an unusual problem to solve. The better you get at building clearly defined services that do just one or just a few things and do them very well, the easier it is to test them with a small set of tests that rely on no outside services. The real difficulty of testing is when you decide that you want to run integration tests among a set of services together. This is one of the areas that DevOps again comes into play and requires some knowledge. You'll need to set up an environment where you can run specified versions of each service, connecting them together with some mock data and run tests against them as an application. It's certainly doable, but it does take some time to orchestrate, and a lot of people for that reason simply choose to put more time into developing their services in a way that they can be tested independently. And again, it's worth noting that the enhanced individual service stability of microservices often means that those integration tests just aren't required. So there you have it. That's kind of microservices in a nutshell. After a decent bit of experience in the pattern, and with a good deployment tool such as Docker, most developers find themselves really never wanting to go back to a traditional monolithic application. While there are areas that certainly do require a little more work, the benefits tend to make for a much more stable application that's much more enjoyable to build and scale over time. To help you understand why Docker and microservices often get talked about together as if they were the same thing, I want to take a little bit to talk about why Docker is the perfect fit for microservices. So let's start by looking at production and then local advantages. First off, there's some production advantages that are huge. One, containers can build very quickly and start nearly instantly. Also, you can create and scale services without adding more servers. Once your infrastructure is in place, all it takes to add a new service is simply run more containers across that infrastructure. And containerized apps also make creating new or one-off environments very easy. Simply spin up some really dumb servers that have Docker on that and run as many containers, any versions of containers as you want. If you want to make an environment just for a specific test case, you can easily spin that environment up, run things across it, spin that environment down. You could also run a complete pseudo environment on your production infrastructure. Simply run different versions of different containers and link them all together. Also, provisioning new services is extremely simple. As you've seen, here's what a Node.js Docker file tends to look like. That's about as complicated as it tends to get. You may have 5 or 10 more lines, but it's rarely any bigger than that. If you're using a compiled language such as Golang, it can actually get drastically simpler. Here's a Golang Docker file. You start from scratch, add your binary, and run your binary. That's extremely simple, and as you can imagine, it builds very quickly. And then here's one of the most complex ones. This would be a PHP Nginx Docker file, and it's still really not that bad. 44 lines of code, extremely simple to read and understand what's going on if you know server administration at all, and it's just easy to provision a complete image for running a PHP environment. So that's about as complicated as that gets. Let's look at some local development advantages. First off,
It's very easy to run many services locally on your own local Docker virtual machine. It's easy to run 5, 10, 50, or 100 services all at the same time. Now, if you wanted to do this with virtual machines, such as Vagrant or something like that, it doesn't really work very well for microservices because it's really hard and painful for your local development machine to run 100 different things at once. You basically have to go one of two directions. You either underpower your virtual machines so you can actually afford to run them all, which gives you a really bad idea of how it will all work when you're on production, or you have to adequately power those machines, leaving your local development machine highly taxed and possibly running very poorly. Whereas again, with Docker, simply it's easy to run many, many services. Also, running service dependencies is very seamless. Docker Compose makes it easy for each service to require as few or as many support services as it wants with no overhead. As you can see, here's a Docker file that has our web instance easily depending on Postgres and Redis. If the next service I work on doesn't require these, I can easily stop all of these services and start the ones required to work on another service. Also, if I add any other services that were dependencies that are maybe services my company owns, I could easily add 5, 10, or 50 supporting services to this Docker Compose file. While good microservices design means you don't often have to run any supporting microservices, you're still capable and able to do it very simply. You also have fewer boundaries when you're using Docker with microservices. You can use multiple languages, frameworks, and databases for one, so you have a truly polyglot setup should you desire. If you have an expensive computational service, you can use a more low-level language, whereas if you have other services that don't require that low-level power, you can use something more scripted. You can choose the correct language, the correct database, the correct framework for each piece of your application. You can also connect multiple cloud providers to the same overlay network. You could have AWS servers side by side with DigitalOcean servers, and it's not difficult to do because overlay networking allows them all to communicate. You're really just not locked down as much to having to have everything run in exactly the same place. It's also really easy to run one-off support services. Say you're building a microservice and it would really benefit from having Kafka running alongside of it. If you weren't running Docker, you'd have to provision a Kafka server, get Kafka up and running, and then connect that to the service you're building that wants to use Kafka. Whereas with the Docker Compose file, as you saw earlier, it's simple. Just run Kafka and connect the two. And then when you're ready for production, just run a Kafka container and connect the two. It's about the same way. So there you have it. There's some quick wins on why Docker is really the perfect fit for microservices. There's a lot of production as well as local development advantages for it. And if you're doing microservices, it really should be your default tool of choice. So you've seen past all of the hype and you've still realized that microservices are a great solution. So you're ready to start building some. Now, before we do, let's first cover 3 quick goals to make sure your microservices are successful. First off, we want your microservices to be fast to deploy, which means they need to build quickly. That means that tests need to pass very quickly and dependencies need to load very quickly. After the build process is done, we also want your application to start very quickly. That means that any compiling that has to happen in order for it to start should take place during the build process. And lastly, you want a lightweight overall image size. That way, when a new server has to pull your image before it can run containers, the pull is very quick. The reasons you want these goals is they make continuous deployment not just possible, but they make it awesome. There's nothing better than merging code to master and having it running in production in no time. It also makes it quicker to verify the results of your new features, and should things go wrong, it means there's less downtime as you push those new fixes live. Okay, goal number 2 is we also want it to be highly decoupled. That means that it can run, test, deploy, and scale completely independently. It also means that we don't want to require any other services to develop locally or deploy to production, because when you get those interdependencies and that coupling, it causes things to just get messy over time. And by other services, I mean other services within your application, because many, if not most services do require at least a database running alongside of it to be able to operate. So I'm just referring to coupling with other services that your team is developing. And lastly, we want it to stay operational even if the other services experience downtime. This is a critical advantage to microservices, and if you don't take advantage of it, you're kind of missing out. The last goal is you want your microservice to be able to own its own data. That means that it has its own database, or at least it owns tables on a shared database, and we don't let any other services touch them. Also, Your service does not directly access data that belongs to other services. You consult the other services when you need a piece of their data. Now, this is easily the most complicated part of microservices, and it's also something that usually has to be figured out. So many companies don't start with this third goal in place. They have to get the services running and then figure out strategies and methods to kind of further break down those couplings in the data. But nevertheless, for new projects, it should definitely be on the goal list for every service to own its own data. So there you go. There's 3 quick wins to make sure that you enjoy your microservices journey as much as possible. In this video, we're going to cover how to make the journey of starting with a monolith and breaking it up into microservices. And honestly, there's going to be a lot of great pointers in here for just starting off from ground zero with microservices as well. But it's really a journey, and often a painful journey, to break up a monolith, even though companies do it because they know it's the only way to move forward. So I'm going to try to share some lessons learned and some best practices of how you can go along this journey. The first step, which may seem counterintuitive to some, is really to identify the discrete data sets. Data is really the center of an application. Function really surrounds data. And if you think about it, almost all applications out there are really about exchanging of data, exchanging of ideas. Function is really about data in almost every circumstance. So data is the center of any application, and decoupled data is as important to your app's stability and maintainability as decoupled code really is. Tightly coupled data between services makes maintenance very hard and very error prone as things change. So nimble and discrete data structures are really every bit as important as building well-organized code in a nimble framework. One way to help you figure out your data sets is to think of the human departments in your business. If you're an e-commerce business, you probably have a shipping department and a marketing department. Now, shipping would care about orders, namely product IDs, quantities of each, and maybe the weight. Marketing, however, cares about product name, product description, photos, and keywords, etc. The data for your application services more than likely needs the same separation that the departments need. Shipping doesn't need to care about all the product name information detail, just the orders, the IDs, and the quantities and the weight. Let's look at a visual example for more details on these data sets. You can see here that each service might manage its own data. Some services, like the client UI, won't have any access to any data at all. They simply interact with other services. The orders service might need product IDs, but it never needs to store the product detail, or even access it for that matter. So product ID can simply be passed around and stored in each database unique to each service. Orders also doesn't care about product descriptions and reviews, but it sure does care about quantity, product ID or SKU, and maybe even product size and weight. If Orders receives that information in a request, it can store it in its own database, and it never needs to talk to the product service. This results in a small amount of duplicated data, namely size and weight values, but it's a kind of duplicated data that's not likely to cause problems since the weight of a product doesn't really change over time. So think about it, because carefully selected data duplication can actually be a huge key in making your microservices architecture really shine and work well. So don't live under the mindset that duplication is always a bad thing. Sometimes it's actually what enables you to do your job very well. So once you've established data, it's time to think of the services that will consume that data and how they'll communicate. So we begin by asking, what services and actions must be synchronous? If it's a synchronous action you need to make, it'll probably communicate over HTTP, probably REST. Now, if there are any services and actions that can be asynchronous, you want to identify those, because those can communicate in a completely separate way that really decouples them from the rest of the application. If an action can be asynchronous, you can simply post that action to a messaging queue, such as RabbitMQ, Kafka, ZeroMQ, etc. And then that asynchronous task can pick up on it periodically, or in real time, it can pull it off the messaging queue, but the rest of the application simply posts the message and moves on with business immediately. Also, once you've identified communication, you want to plan for uptime amidst service failure. This is a huge opportunity if you take advantage of it with microservices. Let's go back to our example again. In this example, shipping really has nothing to do with our client's user experience, so we could make it asynchronous. Orders could either fire off an asynchronous event to shipping, or they could post to a messaging queue that shipping works off of. And remember, we're talking about planned downtime as well. Remember how our orders service is storing a few pieces of duplicate information about each product? Well, that means that if the product service goes down, The orders and shipping service can keep moving on as if nothing has happened because they never have to access the product service. So that little bit of duplication allows for a high degree of decoupling and can actually significantly increase your application stability. It's worth it in this case. In a similar manner, if the recommended service goes down, the product service, which returns recommendations for each product, can simply return no recommendations, log a silent error that the user will never see, but the development team can pick up on that error and fix the recommended service. So the result is no downtime, even though there's some level of downtime. What would normally take down an entire application has simply taken down a feature of your application. So then it's time, once you have your data and your services and the communication figured out, if you're breaking apart a monolith, successfully start with one service at a time. I would identify services that have the most well understood boundaries or services that have been the biggest pain points periodically, things that tend to break easily as you're maintaining the rest of the stack. And those are the ones I would start with. I would build a service, pull one service out, try to get a successful deployment where everything still works with that service out. Lots of times you'll find that as you deploy that service and then deploy the rest of the stack that things break because there was unintentional coupling that you weren't aware of. You'll make fixes, you may have to go back and forth a few times and then really get it working. So once you have that service done, you can either break that service down more if you want it to be a little more micro than you initially started off, or you can move on to the next largest service that you want to take care of. And again, services don't have to start off micro. Sometimes you know you just need to get a large portion of functionality out of the monolith because it's causing problems. Pull it out, get it into its own service, and then maybe from there you can break it apart more. Also, separate databases might have to come in a second phase because lots of times as you're breaking apart a monolith, the data is just too coupled to separate services. And then once you've gotten the services broken out, it can be a little bit more doable to break the data into separate databases. And lastly, don't wait on DevOps. Figure out your core workflow up front. That way, every new service can start off with a boilerplate and doesn't have to be upgraded later. Anything you solve at the beginning of your project, every new service can take on immediately. If you wait on getting a really great DevOps workflow, then you have to take the time to re-implement that new workflow into every other service that's been created. So it's really worth it to figure out a large portion of that core workflow at the beginning of a project with microservices. While it's inevitable that there will be change to the workflow over time, you want to avoid as much of the quote-unquote upgrading, so to speak, as possible. And as a reminder, DevOps almost always saves more time than it costs. It's as if you're in a car race and you take time to put in a bigger engine, it's going to catch up by the end of the race. It's always worth it. So there you go. That's kind of some key pointers to help you out along the journey of breaking your monolith into a bunch of microservices. Have fun doing it. Enjoy getting through the pain points because it's going to be worth it in the end.
Docker infrastructures have a big new piece. Well, it's really not that new. It's been used by the larger companies for quite some time. But that piece is service discovery. Once you get containerized deployments down, the next level of improving your application is to make all of the architecture disposable. Disposable meaning that everything is dynamically configured, so you can destroy a server or a container, simply run a new one in its place, and everything just works. This dynamic configuration is powered by the concept of service discovery. If you haven't used service discovery before, it's a little confusing at first, but it really isn't that complicated once you learn it. To learn about how service discovery works, let's take a look at a simple load balancer. Now, the load balancer's job is to send traffic to all three web instances. Traditionally, you would do this by writing down the IP address of each web server and then configuring the load balancer with those three IPs. If you wanted to add a fourth web node, then you also have to update the configuration of the load balancer and redeploy it. So a change requires a deployment of your web node and a deployment of your load balancer. With continuous deployment in Docker, however, this pattern doesn't really work because each web instance gets destroyed and recreated every time a deployment takes place. So it may or may not have the same IP address or port. So the load balancer needs a way to always know which nodes are available in real time, and it also needs a way to reconfigure itself, and that's where service discovery comes into play. To implement service discovery, we simply run a registry service. The most popular registry services used today are etcd, Consul, and Zookeeper. When web containers start, they notify the registry service that they exist, along with IP address and any port information that would be relevant. The load balancer, in turn, watches that registry for changes. When nodes add or leave, the load balancer notices and reloads its own configuration. This means that if we want to add web 4, 5, and 6, we simply start the containers up and register them. The load balancer, along with any other services that depend on them for that matter, will automatically know that they exist and reload themselves. So to go from 3 to 6, we simply start 3 more and register them. To make things even more decoupled, we can run a Docker container called Registrator, which will automatically watch for all Docker containers and automatically register and deregister them when they start or stop. Now our web instances don't even have to be aware of the registry. Registrator takes care of that automatically. So to go from 3 to 6 now, we simply start 3 more containers of web. With all this in place, we can now run multiple copies of our load balancer across multiple Docker machines for an additional level of failover. If we have a 4-machine cluster, shown here by the 4 rounded rectangles, we can run 2 copies of the load balancer and set up DNS to fail over between them if one machine goes down. Since each load balancer configures itself by watching the registry and load balances all available web instances, the traffic will continue to flow undisturbed if a complete machine with a load balancer on it goes down. One of the key ways that this works is because Docker allows us to create an overlay network between multiple machines. One of the great things about the overlay network is that each container gets its own IP address, so that when containers need to communicate, they can access each other by IP address directly. Containers don't have to expose any ports on their machines anymore as well, so the communication can happen direct from container to container, which makes it much more secure. Perhaps the best thing about this is that our servers just became disposable as well. If we start having issues with a machine running Web 2, we can simply destroy it and attach a new one to the cluster. Web 2 will either be rerun on another machine or will start up on the new machine, and when Web 2 is running again, it will automatically start receiving traffic. So as you can see, we have 3 main pieces to service discovery. We have to be running a registry service, and then services need to register themselves, or we need a way for them to be automatically registered. And then the third piece is that services watch the registry and reconfigure themselves when things change. So that's simple enough, isn't it? With a few small pieces in place, our infrastructure can now grow and shrink with no additional configuration. Every single piece can start, stop, change locations, and everything just works. It's well worth the effort to put service discovery into place. In this video, we're going to use etcd as a service registration and discovery backend. etcd's place in the registration world is a very straightforward and simple one. It's essentially a key value store, so it'll act and feel a lot like Redis if you're used to using Redis. Basically, it also clusters and can do distribution very well. So failover can easily be covered since you can run 3 versions of etcd on 3 different nodes, and that way we're covered in case a node goes down. For this case, we're just going to run a single etcd container, and then we're going to play around with it so you can see how service registration and discovery will work. We're going to begin by just running a Docker image for etcd. We're going to expose port 2379, so that way we can actually look at it in a web browser. There we go, it's running in the background. So now we can go to localhost port 2379 and version 2 keys. You can see that no keys are set, and again, it's a key value store. So now we can go ahead and post some keys here. I can also run a GET request over here. I'm using the Chrome extension Postman, so that way you can visually kind of see the request that we'll be making. So let's go ahead and do a put to keys, web, upstream, 1. Now let's go ahead and give it a value. We're going to use the www form encoded, and we'll just give it a value of, let's see, we're doing a web upstream, so this should probably be an IP address. Well, let's just do 1.2. Let's send it, and there we go. So now if I were to refresh, you can see I have a root level key of web. So then I can go keys web, and I have web upstream, and then I can go web upstream, and you can see that I have web upstream 1, and I have a value there. Let's go ahead and post web upstream 2 now. Let's say a second web is running, and it also makes a put command here that, hey, I'm running too, and I have an IP address of 3. There we go. So now if I refresh keys web upstream, you can see that I have 2 nodes currently active here. So that's kind of how you'll add nodes. And then deleting is also very simple. I can do a delete request. I'm just going to send a delete request to upstream 2. And now if I refresh, I simply have upstream 1. I can also do a recursive here. So if I want to maybe add some more configuration to web, let's say web is always going to use port 80.
for all upstreams. There we go. Web port 80. Then I can go web there. You can see that I have port 80 and I have upstream, but I also want to see all the information on upstream. So I can add a recursive true flag. So now I can get the entire configuration for my web service. I can see that it's got a port of 80. I can see all the upstreams that are there. Let me go ahead and put that second upstream there as well. Again. And give it an IP address again. Let's just make something up. There you go, it's been added. So you can see now I have 2 random upstreams with 2 random IP addresses, and they'll always use port 80. So that's kind of how you'll create some configuration. And then you can also optionally delete an entire service if you'd like. I could just send a delete request to web and use that same recursive true flag. And there we go, all of web is now gone. The entire key is not found. Another great way that you can access etcd is through etcd control on the command line. So since I have that etcd container running right there, if I run docker ps, you can see I've got a container that I've named etcd. I can actually get a shell script in there, and that has etcd control available for me. So there you go, I'm now inside of that etcd container, and I can use etcd control to do the same operations. Let's change this IP address to 222. There we go. And now I can refresh over here. And I've got the web upstream 1 is set. And I can also get things here as you'd expect. I can get web upstream 1, delete web upstream 1, all the things that you'd expect. There we go. So etcd control is also a great way to interface with etcd. Also, if you're using any popular language, you can set up a watcher on etcd as well, and you can watch any directory or any endpoint. So that would be how a load balancer would watch etcd, get reconfiguration changes, and automatically reload itself as things change. So there you have it. As you can see, etcd as a registry backend is extremely simple. Services with one command can register that they exist, with one command can deregister, or they can even set a TTL, which means that that service will time out after, say, 60 seconds. If I don't continually post that I still exist, within 60 seconds, take me off the list. So services can easily register themselves, and it's extremely simple to get a configuration for a service and behave off of it. In this video, we're going to explore using Consul as a service registration backend. Now, Consul is extremely full-featured. It provides a lot of functionality, which means the learning curve is slightly more than you'd find in a more simple key-value registry like etcd, but for many people, the feature set that you get in the long run pays off. Let's begin by running a simple Consul container. With Consul, you'll usually want to run more than one container, so you have failover, but in this case, we can simply run one, and it's extremely simple to work with. So let's go ahead and run a Consul container right now. We're going to expose port 8500. And then Glider Labs has a great Consul server container that we can use. There we go, our container's running. So now I can go to localhost port 8500. And you can see that out of the box, they give me a great UI. I can see that I have one node running, and I have one service running on that node, which is Consul. It also has a key value store, should I want to create keys. There we go. I've got a key called test. Let's update it to test1. And then I can also do services. So you can see already it's made to be much more of a service registration store instead of just a key value store. So let's go ahead and add some services with Postman as well using simple HTTP posts. The 2 endpoints you're going to use are v1 catalog register and v1 catalog deregister. And you're going to post to JSON objects. So let's go ahead and get our first JSON object going. By default, you simply need 2 values. You need node and address. Let's go ahead and say a new actual machine spun up and joined our cluster, and it's going to register itself here. So it needs an address. And let's make one up. There we go. And let's go ahead and send this over. So now, if I were to refresh, you can see that I have 2 nodes. I have my one node running Consul, and I have another new node that's currently running no apps. Let's go ahead and add an application to it now. Application, I simply need service. And then at the root level, all you need for service is an ID and then a service name. So this will be web1. and then the actual service will just be called web. So if I were to add 3 IDs, web 1, web 2, web 3, I'd want to make sure the service was always called web, so they would be grouped together. Let's go ahead and send this over. You can see that apps is now running one service, and that service is called web. Now I don't really have any useful information on it, so I'm also going to want to add the address and port number. There we go. So let me go ahead and refresh. You can see I'm still just running one service. It automatically updated when I hit register because my ID was the same. Whenever you use this ID, it will update or it will create. So it's a create or update. And then there we go. I'm on IP address 222.22.22.2, port 80. Let's go and add a few more copies of our web app now. We're going to register web 2, which is an IP address of .3. We're going to register web 3, which is an IP address of .4. And again, I kept service always as web, so they'll be grouped together as a part of the web service. And on refreshing my GUI, you can see that the apps node is running 3 instances of my web app, and they have different IP addresses there as well. I could also register these on another node. Let's say apps 2 is spun up with a different IP address, and it's running web 4. There you go. On refresh, I have 2 nodes now, apps and apps 2. And then I also have 1 service on apps 2 and 3 services on apps. I can also use the HTTP API here, and I can do catalog services. You can see that I've got 2 services, console and web. So then I can go to service, web. And you can see that web has 4 running services right there. And it's going to show you which node they're on, and that's going to also show you the service address and the port for each service. So that's console in a nutshell. Let's go ahead and use the deregister functionality now. Simply change this to deregister. And all I need to deregister a service is the node and the service ID. So I'm going to remove node, apps 2, and I believe that was web 4. There you go. Yep, web 4 is gone. Let's go over to our apps node and remove web 3, web 2, and we'll leave web 1. So there you have it. That's how service registration and discovery will work with Consul. Consul has a lot of features. As you can see, it has data centers, so you could do registration based off of data centers. You could completely do this with your own custom key value store as well, but having it built in and baked in kind of makes sense for a lot of people. And you gotta admit, having that great user interface really does make the barrier to entry a lot easier for Consul as well. So that's Consul in a nutshell. Hope you enjoyed it. While deploying single Docker containers across single servers really simplifies things in the deployment process, Docker really begins to shine when you deploy multiple applications and containers across multiple nodes that are all networked together. In this video, we're going to use Docker Swarm to set up a standard Docker Swarm network of multiple nodes that we can deploy our applications across. It'll give us high availability failover and the availability to continue to scale applications without necessarily scaling our infrastructure. Let's begin by using DigitalOcean because this will keep it very simple and very straightforward. I don't want you to worry as much about which cloud provider you're using as much as I want you to worry about what kind of infrastructure you're building. And you can pretty much do this on any cloud provider. So DigitalOcean is fast and simple. We'll start here. And for this, we're going to make 6 servers, or they call them droplets. So let's go ahead and spin up 6 of them. And to make it simple, they have a one-click app which already has Docker installed. There we go. I'm going to go down. We'll use New York. It's important that they're networked so they can talk together. And I'm going to give them one of my SSH keys here. And then let's go ahead and create 6 of them. I also want to rename them to different things. We're going to have 2 of them that are our swarm managers. And we want 2 of them because we want one to be able to go down and fail over. So we have swarm manager 0 and 1. And then we also have some that we want to have external load balancing for our applications. These will be publicly accessible. So I'll have 2 of these, so that way I have some failover as well. And then we also want some that'll actually run our applications. And these will be the ones that most likely scale and scale and scale. But we'll start off with just 2 of these, since all it takes is 2 for failover. There we go, 2 managers, 2 load balancers, which will be the publicly accessible parts, and 2 application nodes. Let's go ahead and create these 6. I'm going to save you the time, and I'm going to go ahead and skip ahead to when these 6 are created. There we go. We have 6 nodes created. Let's go ahead and SSH into our manager 0. Okay, there we go. Now, for our swarm nodes to all be able to find each other and discover each other, we're going to need a registry backend that they can all register themselves to, that they'll all have access to. For this, we're going to run a simple Consul container. You can also scale this out to a full-scale, high-availability Consul cluster, and I'll include a link in the working files to show you how to do that. For now, we're just going to run a single Consul node because that'll get us through just fine. We're going to do docker run and expose port 8500, which is the standard Consul port. We're also going to run it in server mode and bootstrap mode. There we go. If I do docker ps, Consul is running. So now we want to go ahead and run the swarm manager as well. And you'll notice right here, I'm exposing it on port 4000. That's very important right there because we're going to access the swarm manager and manage our entire cluster through port 4000 moving forward. Now this is also very important here. We're going to advertise our IP address on port 4000 as well. So there's my IP address. And we're also going to add our Consul address, which currently is this address that I'm on now, and 8500. There we go. Our swarm manager will download and will run. So now we can log into our second manager and run a very similar command. The only thing we're going to do is we're going to keep this Consul address the same because that's our manager 0 where Consul is running. And we're going to change the advertise IP address to be the IP address of manager 1. Let's exit out and do that. Log in. Now let's go ahead and copy that very long command and just change the IP address. So we're keeping, again, the Consul IP address is the same. That's the only place it'll be running. And recopy this new manager 1 IP address. Oops, need a space in there. There we go. So our new manager is running now. So we have 2 managers running. Let's go ahead and connect some nodes now. I'm going to copy this IP address, and to make it simple, I'm just going to do it in one long command. I'm going to SSH in and run the docker swarm command at the same time. So SSH root at, and change this on all your servers to not log in as root. You'd want to create a less privileged user, and you'd also want to harden the servers. I'll talk a little bit more about some things you want to do here later on in this lesson, but for now, let's get the swarm up and running. So we're going to log in, and then we're going to run docker run swarm. So this won't be running swarm manager like up here. We're going to be just running swarm. There we go. We're going to join. We're going to advertise ourselves on port 2375, which is the standard Docker port. So there we go. That's the IP address of our current node. And then we also want to register to Consul again. So let's copy Consul from up here. And there's Consul. That's how we're going to find each other. And we're good to go. Let's go ahead and run that command. There we go. We've logged in and we've run that command. Now let's go ahead and do this on every one of the nodes. For simplicity's sake, I'll just copy and paste and replace those IP addresses. So that's our LB. So we're logging into LB1 right now and running the exact same command. Excellent. And we'll do this 2 more times. App 0 and app 1. While that's running, I'll copy our IP address. So it feels like quite a bit, but we've really just essentially set up 6 servers and we have a complete cluster ready to go. We could realistically deploy a handful of applications across this cluster and everything would run fine and we'd have failover for all those applications. So let's go ahead and log into that manager 0 node again and let's look at our swarm. So I'm on the manager 0 node now and I can go docker H:4000. So I'm using Docker with a host on port 4000 and let's get our info. We have 4 nodes here. We have swarm running, but all these nodes are in the pending status. That's because we cannot connect to the Docker daemon on these hosts. We haven't exposed it yet.
So one more step is that we have to log into each one of these Docker hosts, and we have to edit to expose the cluster and advertise our IP address. So let's go into swarm LB 0 and 1 and app 0 and 1. And the file you're going to want to edit is /etc/default/docker. Now, if you take a minute to look at the working files for this course, you'll see a very long command that I want to go ahead and copy and paste now, because I don't want to have to bore you with typing the whole thing out. It's this long docker ops command that I just pasted in. So you'll essentially be advertising your cluster on your Ethernet 1 IP address, port 2376. You're also going to connect to Consul again, and again, that manager 0 IP. So let's go ahead and copy that manager 0 IP, and let's paste that in. And then we're also going to be exposing some ports. Now, it's very important at this point. Those other things that we're doing are going to open up the ability for overlay networking. So we can have a network and all the containers on the nodes can talk to each other across nodes. But it's very important to mention at this point that you need to lock down port 2375 from external public traffic. Anyone at this point with access to port 2375 will have access to your cluster and will be able to cause a lot of damage. So if you're on something like AWS, they'll probably call it a security group, is what AWS calls it. Or if you're on something more bare bones and straightforward like DigitalOcean, you'll want to implement IP tables or a firewall, a software firewall of your choice. So that way you can allow port 2375 to have internal traffic between your nodes, but you will want to lock it down from external traffic outside of your nodes. So I've made my statement about that. At this point forward, there will be a vulnerability risk on the cluster I'm presenting to you, and it will be on port 2375. So let's go ahead and exit out, and we just need to restart Docker. There we go, Docker's restarted. Within a few minutes, my node will now be available on the swarm. Behind the scenes, I'm going to go ahead and add all 3 others, and I'll come back when you can see all the other instances are available on the swarm. So I've gone ahead and changed that configuration, added the Docker ops to all 4 of my nodes. Let's go ahead and SSH back into that manager 0 again. Again, let's go Docker host 4000 and info. There you go. You can see that the first one I've added has already showed up, that's swarm LB0, and the other ones are still pending. It'll take a few minutes for them to show up. What we're seeing is that they've registered just fine to Consul. These are all their IP addresses and their port 2375s. However, that Docker daemon is not exposed yet, so it's not able to connect to it. That'll all change in just a few minutes as it updates with Consul and gets another look. Okay, it's a few minutes later, and if I run docker h port 4000 info now, you can see that all nodes have joined the cluster, and they're all showing up as healthy. Swarm LB 0 and 1 and swarm app 0 and 1. I can also run docker ps on this, again, port 4000, and you can see that no containers are running. Now that's different from just running docker ps on my machine, which will show you the containers running on the swarm manager machine, this machine that I'm logged into. But that port 4000 PS will show you all of the Docker containers running across all of your nodes because that's the Swarm Manager port that we're logging into. So there you have it. We've got our cluster set up and we're all ready to run containers and applications across it. We have a Swarm cluster up and running. What we have here is 2 Swarm Managers for failover. We have 2 Swarm LBs, we're calling them. These will be our publicly accessible load balancers that we'll be able to use to access internal applications, containers running that we don't want direct access to. And then we also have, for now, just 2 app nodes, app 0 and app 1. So let's go ahead and run and schedule some high availability applications across these nodes. Let's begin by SSHing in to our manager 0. So we're logged into Swarm Manager. We can go docker h port 4000 ps. We have no containers running across our infrastructure. So let's go ahead and run some hello worlds. The Docker Cloud Hello World container is a great example for hello world. Whoops, I forgot my run command. Gotta make sure I include the run commands. So docker h port 4000 run, and then all of my usual Docker run arguments. There we go. Let's go ahead and now run hello 2, 3, and 4. So now if I were to scroll up and hit that docker ps command again, you can see that I have 4 hello worlds running. And it doesn't just tell me the name of it, it also tells me which swarm it's on. We have on app 0, we're running hello 4. On LB1, we're running hello 3. App 1, we're running hello 2. And on LB0, we're running hello 1. Excellent. Now, if we want to communicate with each other, it can get a little bit tricky though. I can't really access this very easily, so we'll actually want to create a network that we can use to communicate from container to container. Since we've set this up for Docker networking, creating a network is as simple as doing it on your local machine. We can just do a network with an overlay driver, so let's choose driver overlay. And this is going to be an internal only network, and we can optionally also include a subnet as well. Let's make this 0.9. There we go, and let's call this apps. There we go. So we've created a network called apps, and if I were to do docker h network ls, you can see that we have an apps overlay network. You can also see all the swarm networking that's going on. So now we can schedule some applications across that apps network. Same thing pretty much as before, except we're going to add an apps network. So I've added hello 5, and let's go with the exact same command, run hello 6. Now what's interesting here is now that they're on the same network, hello 5 and hello 6 can access each other by name. Let's open up a shell inside of one of these containers. Let's get into hello 5 and let's open up a shell. There we go. So now I can ping directly by name hello 6 because the networking has provided a host entry directly to hello 6. You can see its IP address 10.09.3. Let's go ahead and exit out. Let's do the opposite thing. Let's get into hello 6 and see if we can ping hello 5. Same thing, we just have a different IP address, 10.0.9.2. Now let's go ahead and try to ping hello 4. You'll notice that it hangs. We cannot communicate with hello 4 directly because we're not on the same network. Let's go ahead and exit out, and let's, just for grins, let's log into hello 4 and see if hello 4 can ping hello 3. Hello 3, a bad address. You'll notice that host-style networking is not enabled unless you're in an overlay network. That's one of the big key features that makes the little added extra effort of getting an overlay network set up totally worth it. So this will be the most basic way that apps can communicate with each other, is directly by host name. If it's a one-to-one relationship, you don't need to do any kind of linking, any kind of connection, just have them communicate with each other. Let's clear our console and show you a little bit more of a realistic example. Let's say hello 5 needs to make a RESTful API call to hello 6, an HTTP request. Let's go ahead and get back into hello 5 here. So we're inside hello 5. Let's say we just wanted to do a GET request to port 80 on hello 6. The command for that would be in wget would be O and then the extra dash. Again, we can just call hello 6 and then port 80, and then there would normally be some API, but in this case all we have is port 80. So there we are. You can see there's our hello world HTTP HTML document. It's successfully connected to hello 6 without even trying. As long as we know the name of the service, we can communicate directly. Now this doesn't work very well for load balance scenarios. If we have 7 copies of hello and another service needs to make a load balanced request to that, this won't work very well. We will need to scale it further up and add a little bit more tooling to get that to work the way we want it. But for smaller sized applications or applications that have a one-to-one relationship, this works extremely well. Now what we need to do is be able to target specific applications. Let me exit out again. You remember on port 4000 PS, you'll see that these are automatically just showing up to any single node. We have some showing up on the LB node. It's wrapping around, so it's a little difficult to see there. But we have some hellos showing up on an LB node. Some hellos are showing up on an app node. The next thing we'll want to do moving forward is we'll want to actually add some tags so we can target specific applications to specific nodes. In this video, we're going to add tags and constraints to specific nodes so we can target containers to a grouping of nodes that we want them to run on. We still don't have to care about which specific node it runs on. Nodes can still be destructible, completely replaceable, but we do want to be able to tell containers to run on a certain type of node. There are several use cases that are common with that. For one, we want to be able to have different types of security across different nodes. In our application nodes, for example, we don't need any external traffic to have access to any ports at all. They're going to be running applications internally, and then load balancers will balance traffic to them. Those load balancer nodes, however, definitely need at least port 80 and port 443 for SSL traffic to be able to get through from public access. So we will want different security across different nodes, different security groups, so to speak. And then also, we may have different types of nodes that are suited for different things. Some may have higher memory, or some may have a different type of hard disk. Some may have more processors or less processors, and we'll want applications to end up on a certain type of node. Tags really allow us to do that and add constraints to the containers when we run them, and then the Docker Swarm Manager scheduler will automatically run them in the correct place. So enough talk about that. Let's go ahead and get into some of our nodes and add tags. Let's start by going to the app nodes. I'm going to copy that IP address, exit out of the manager, and let's get in there. There we are, we're in one of the application nodes, and we're going to edit that etc default Docker file again. And we're going to add a little bit more information to the command. We're going to go ahead and on this Docker ops command, let's go ahead and arrow key down there. We're going to add some labels. So there we go, type equals apps. And let's say this one's also only for production environment. There we go, so we've simply added two labels. Actually, I'm going to use another label here. That's not quite correct. There we go, have two labels. Let's go ahead and save that, X out of it. And let's log into our other app node and add some as well. In this one, we're going to add environment equals staging. Let's go ahead and save that. And we also need to reboot Docker, which I forgot to do on the other one. So restart Docker. Good. Now, if I had made a typo or something wasn't working, that restart Docker command would not work. It would give me an error message. So we know that my configuration is still working. Let's go ahead and exit out. And I'm going to get back into that first node and restart Docker since I forgot to do that. There we go. Both of them work just fine. Let's go ahead and get back into the manager now, and we'll just work with these two app nodes for the rest of this example. So I'm back into the manager. I'm ready to run some containers. Let's do a Docker, our familiar H4000, and let's do info here. Now, you'll notice there are tags here, labels as they're called, for every single application node. But again, our new labels have not showed up. It'll take a few minutes for them to show up. So I'll be back in a couple minutes and we'll schedule some containers across specified nodes. So about 3 minutes has gone by. If I run port 4000 info again, you can see that my apps have received their tags. They have an environment of staging and a type of apps. And down here in app 1, we have an environment of production and a type of apps. So now we can go ahead and we can actually schedule containers with or without a constraint, and they'll end up on the correct places. So let's go ahead and run some applications now that have some constraints on them so we can specify which node they're going to end up on. Let's go ahead and run Docker, run, and we're going to add an environment variable that starts off with constraint and then the tag. So there we have it. We're going to do a constraint with the type of apps. And then let's also tell this one that we want it to land on production. And I also forgot that D flag. I want to run this as a daemon. Background it. Okay, excellent. Let's go ahead and run this a couple more times, hello2 and hello3. So I'm now running 3 copies of Hello World, and let's go ahead and take a look at our Docker PS and see what's running where. You can see they're all running on Swarm App 1. Hello World 1, 2, and 3 all landed on that exact same one. So now if we're going to change this Hello 4 and change that environment to staging, it's going to end up on a staging box. You can see that we have app 0 is where Hello 4 is running. Again, that wraparound makes it a little frustrating to see, but Swarm app 0 is where Hello 4 is running. Let's clear the screen, and as you may have guessed, if we run that exact same command and remove the staging constraint, then it will run across either app node. It will simply find a good app node to run on. So let's run hello 5. Let's run hello 6 and 7. So you can see that hello 7 is running on app 0, 6 is running on app 0, and 5 is running on app 0. That's because we actually have it a little out of balance. There were a lot on app 1. If we continue running these, 8, 9, and 10, they'll start landing on separate application servers. One of the great things that Swarm will do is it'll make sure that you don't overload by default any one server. If you don't specify what it's going to do, it'll make sure that it balances the load around. You can see that 10 landed on app 1, 9 landed on app 0, 8 landed on app 1, and then here are those 3 consecutive app 0 landings that balanced out the weight to both of the nodes. So tags make it great. It's really helpful. We could just as easily have had a tag for solid state disks, so any kind of disk intensive applications could make sure they land on those. We could also have a tag for 8 core or high memory. And likewise, as creative as you want to get, you can really add tags to customize the experience of which containers land where. I want to take a moment now to talk about Docker security. There's some vulnerabilities with our Swarm cluster that we have going on now. There's some standard vulnerabilities, like we're using the root user login, and we haven't set without password to the root user. So that should really be set. So that way you can't even try to log in as the root user with a password. You have to use the much more secure SSH key. Also, ideally, port 22 would be restricted to a whitelist of IP addresses, because that's very important. If someone were to gain SSH access to one of our key nodes, they could really shut down all the applications on our whole cluster. So you'll want to take application security much more seriously with a Docker cluster, because that cluster is all of your applications. It's kind of the equivalent of a network breach. If someone were to compromise the Docker daemon or the Swarm manager, they've really essentially compromised your entire network of applications, and they can shut down all of them or cause damage to every one of those servers. So you do want to restrict a lot more as much as you can with a Docker cluster. But let's look at some Docker specific vulnerabilities which are going on right now in this cluster. Let's go ahead and copy one of these IP addresses to one of the managers. And I can show you here, currently port 4000 can be accessed anywhere in the world. So I can go Docker H, that IP address, port 4000, get info, and there you go. I actually have access to my entire Swarm cluster anywhere in the world. Because if you'll remember, when we ran that command to run Swarm Manager, we exposed port 4000. And by default, Docker's going to expose that to the whole world. So we're going to want to restrict access there. Also, Consul, which is running on Manager 0, is publicly accessible for the same reason. We ran it on port 8500. So there you go. I can actually access Consul's, by default, UI permanently moved, but I can actually access Consul. That's their default response for port 8500 with no path. So that's also a problem. I could cause a lot of damage by messing with service registration and discovery. Also, any one of these application nodes is also vulnerable. Let me grab a load balancer. I can go Docker again, and I can connect to port 2375, the default Docker daemon port, and I can do a Docker PS and see that 2 things are running on this node. I can also run something new. Let's name this Hello 3. And we'll run it as a daemon, so it's not going to be running here in the foreground. There we go. I can run Docker PS again, and now there's 2 copies of Hello World running. So if you remember, we actually had to make that Docker daemon accessible in order to get networking started, but now it's accessible to everyone in the world on port 2375. So we're going to want to lock some of these down. This is one of the reasons that I actually encourage people not to use DigitalOcean by default for Docker. It can definitely be used, but when you're getting to the Swarm cluster level, something more like AWS is a better fit. Whereas with DigitalOcean, you'll spend more time securing all the ports, basically creating your own private network. With something like AWS, you'll spend a little more time learning it, but out of the box, they give you a private network with a lot more security restrictions. So it's kind of the handoff. You have to either learn the tool that provides it for you, or you have to learn the tools and install them and provide them for yourself. Either way, you need to take security with Docker seriously because there's just a lot more vulnerabilities to be aware of. So let's go ahead and use IP tables as a standard way to lock down a lot of these ports on DigitalOcean. I'm going to go ahead and SSH into this Manager 0. I'm going to clear my screen.
And let's start using IP tables. Now, by default, that IP tables command you can use to look at is IP tables, capital L. So here we have some chains going on. You can see there's a Docker chain right here that's exposing port 4000, port 8500, yep, to anywhere, from anything. So that's just Docker's default way of exposing ports when you expose them. It's doing exactly what it should do. So what we're going to do is we're going to add a new chain called Docker security, and we're going to put that chain in front of this chain. So that way we get to actually do a little bit of filtering before people have access to Docker's IP tables chain. But before we do this, we also want to install IP tables persistent, so that way we can save these IP tables rules and they'll persist after a reboot. So let's do an apt-get install and an apt-get update. There we go. IP tables persistent is installed. So let's go ahead and add that Docker security group now. We've created the Docker security group. Let's add a forwarding rule to put this before Docker 0. And it's important that we use I here. If you're familiar with IP tables a little bit, but not a lot, you have an I flag, which inserts it, prepends it to the top of a chain, and you also have the A flag. This would add it to the bottom. So in this case, we want it to be one of the first rules that happens. So we're going to add our forwarding rule with an I, and then we're going to forward Docker 0 to Docker security. There we go, that's been added. Now we can go ahead and add some rules. I'm going to go ahead and copy and paste them. I've also included them in the working files, but I'll copy and paste them here so it's a little bit quicker. You don't have to watch me type them all out. There we go, I've added 2 rules. The first rule says that I'm always going to accept port 8500 from Ethernet 1, which is my internal IP address. So that way any internal nodes have access to 8500, which is Consul. And then I'm going to drop connections on any other port with a port range of 1025 to 65535, because there's really no reason that anybody else needs to access this. Internally, I will still have access to Docker H port 4000, but any other nodes will not be able to do that. So if I want to control the swarm manager, I have to SSH into the swarm manager node, and then I can control the swarm manager. Now all I have to do is do an IP tables persistent save. They're saved, so on reboot, this will persist. Let's go ahead and exit out and see if I can connect to those 2 addresses anymore. This is exactly what we want to see. The connection gets dropped as soon as we try to make it, so it just hangs. Let's also try that curl command to port 8500. Excellent. Again, it just hangs. So we've locked down this node a lot more. Now, it's important to point out that on DigitalOcean, there's still one more vulnerability. When you select private networking, every other private networked node in all of that data center has access internally. One of the biggest weaknesses with trying to do Docker networking and private networking on DigitalOcean is it's not just your nodes that have access on an internal level. So this is one of the benefits to AWS. You truly do have a virtual private data center. And that data center, your nodes are the only nodes that can see you, and all the other nodes can't see you, no matter who they are with. So next up, let's go ahead and log into one of these LB nodes so we can lock down port 2375 so that Docker daemon will be secure. Again, we're going to install IP tables persistent as a first measure. There we go, IP tables persistent is set up. So then I'm going to add 2 rules. One rule, only allow port 2375 access from our internal IP address, and then we're going to drop every other connection. I'm going to go ahead again and copy and paste these from the working files since there's some pretty long commands. There we go, there's our 2 commands. One to allow port 2375 access from our Ethernet 1 address, and another one to drop all other connections to port 2375. Let's do this, and let's go ahead and save them persistent so they'll persist on a reboot. Excellent, they're saved. Let's go ahead and log out and see if we can connect again. Excellent, it hangs just as we would expect. So there we go, we've shut down a lot of the security. We've really tightened things up. And then the one thing we're going to need to do here is we're going to want to go ahead and log in, and we're going to want to stop our swarm and our swarm managers. And we're going to want to restart those advertising the correct Ethernet 1 IP addresses. If you remember, when we started our swarm and our swarm managers, we had an advertise flag in there where we had to do our public IP address. You'll see this in your working files. Well, that's not going to work anymore because the public IP addresses are no longer available on port 2375. You're going to want to log in and get your Ethernet 1 IP address and advertise that instead. So that's going to be the way that you continue to keep your security tighter. Or again, if you're using something more like AWS, you'll simply use a security group to lock down access to all of these nodes. That's kind of some basics on Docker security. Those are the ports you're going to really want to look out for. And again, if we are looking at our nodes here in our swarm, we could lock down all the ports on these. No one really needs to access them. Internally, we need 2375 available, and that's about it. Swarm load balancers, they're going to need ports 80 and ports 443. And then the swarm managers really don't need anything except for that console port 8500 available. And that console port 8500 just needs to be available internally to the others. So it's worth taking the little bit of time to really figure out that Docker security before you start launching applications into production on it. I hope this helped you out. In this section, we're going to be implementing some fun service discovery patterns, automatic service registration, dynamic load balancing, and other things. And there's so many ways to do it, but real quickly before we get into it, I want to show you a couple of the patterns that we'll be doing so you get a visual overview of what we're going to be putting together. This will also help the gears in your head start spinning about the ways you would like to implement things for your projects. So here's an example of what we'll be throwing together first. It's kind of the simplest way to go through an automatic service discovery. You have your DNS in this case, which would be dynamically failing over between two Nginx load balancer nodes. That way, if one goes down, the other one starts getting the traffic right away. You might also be able to do DNS in a round-robin fashion to where everything gets the traffic. Either way, there's essentially more than one Nginx front end that's exposed publicly, so the traffic can be either load balanced across multiple nodes or A/B handled in case of a failover. Next, you have your actual web applications running on nodes. In this case, we have web 1, 2, and 3. And then we have a registry. So web 1, 2, and 3 are going to register to that registry. Hey, I'm here, I'm running, here's how you contact me, my address and my port number. Those Nginx load balancers are then going to get updates from that registry periodically and automatically reconfigure themselves and reload themselves. That way, if web 2 were to suddenly move to the other app node, it would trigger itself to the registry and the load balancers could pick up on it. If we add a new app node and web 3 ends up on its own, the load balancers will automatically know. In this first scenario, the web 1, web 2, and web 3 instances automatically register themselves to the service registry. One of the advantages to this is it's very simple. You do have to code two parts to each web application, the part that runs and the part that registers itself, which does add some coupling that may not be desirable, but it is very simple. All you have to do is make each web container aware of the registry and they can register themselves. Here's another way that you can do it, is you can add sidekicks aside each web service. So web 1, 2, and 3 run, and then you'll assign a sidekick next to web 1, 2, and 3. Those sidekicks will notice that web 1 is running and they'll register it for you. Or actually, the sidekick's job is simply to register that web 1 is running. It will periodically make sure web 1 still works, and if web 1 goes down, it could also register that web 1 is not operational. The disadvantages to this is you have more containers and it does get messier. The advantages to this is if you require service introspection for possibly some more detailed health checks that are service specific, the sidekicks may be a good pattern for this. But in general, I feel like sidekicks add a level of complexity that you usually don't want to introduce. The third way would be to add a dynamic registration container. You would add one of these on every single node that you run. So if you have 2 nodes, you'll be running 2. If you have 10, you'll be running 10. If you have 10,000, you'll be running 10,000. Any containers that arrive on that node, the registrator watches the Docker environment and it automatically registers that to the registry. So each registration container is aware of the registry and aware of the containers on its node. This is kind of nice in that you never have to worry about registering your applications. You'll maybe expose some environment variables that tell the registrator how to configure them, but that's about it. This is my favorite way of doing things, and while it takes about as much work as getting set up any other way, it just is a lot more fun. It also seems to be a little bit more reliable. If Web 1 again were to move, Registrator would automatically unregister it, and another registrator on another app node would automatically register it. I'm calling it Registrator because the most popular container for this purpose is called Registrator. It's put on by the Glider Labs people, and it's a really useful container. It doesn't work in every single setup, but it is useful in many, many ways. It's also very, very easy to make your own registrator type of container that will automatically register your own web instances to the registry. So I'll show you how to do that later on in this section. Okay, that's about it. Let's actually get into the real fun of putting together service discovery. The first order of business in creating our automated service discovery platform will be to get the registry going. The registry will be where our applications register themselves when they start up, and it'll also be what our load balancers query to find applications to load balance. The first thing we'll want to do is create a network called apps that we can run all our apps across. This way, they can communicate with each other via Docker networking hostnames. Okay, so let's create that network now. And now we're going to go ahead and run an etcd registry across it. I'm choosing etcd because it's extremely bare bones. It's essentially a key value registry, much like Redis, and that makes it very lightweight and customizable. Whereas the other two, Consul and Zookeeper, are a little bit more opinionated. I want to go with something straightforward that I can work with any way I choose. So I'm going to run an etcd node now. I want to make sure that it does always restart in case it goes down. And I'm going to add the constraint because I want it to run on my apps nodes, not my LB nodes. I want to keep my LB nodes as lightweight as possible so the LBs never get bogged down if traffic grows. I forgot to add the run tag in there. So port 4000, run. There we go. etcd is running and I can do a docker ps to verify. There we go, it's running on app 0. So now other apps can access it as long as they're running on the apps network. Let's verify this and kind of test it out by running an Alpine Linux image and installing curl. We're going to remove this when we're done. We don't want to clutter up our nodes. And we're just going to automatically log into the shell. So I'm going to go ahead and install curl now. All right, curl's installed on my Alpine Linux box. So we should be able to curl etcd directly by hostname. And that's going to be v2 keys. Excellent, we were able to communicate with etcd, and we can see that there are no keys there. Let's go ahead and put a key up there. v2 keys. Let's call this one test. And our value will be success. So let's go ahead and get that. There we go. Our test key was retrieved and the value is success. So we're able to communicate with it. If this was a Sidekick service I was in, I could make service request posts. If this was an actual web service and the web service was doing the registration, exact same thing. I can communicate by hostname straight to the etcd container. And same goes for an automatic registrator. I could communicate straight with the container. So now all that's left for us to do is to figure out the kind of data we want to register with our services, run some services, and register that information. So let's say we have a service called web. We know we'll want to know which port it's on. So let's say we'll want to store port 80. And we'll also want to know how many instances of web are running. We could call these instances, or we could call it upstreams. Let's stick with upstreams. Let's say you could either track it by IP address, or you could also just track that this one's called Web 2. Since Docker networking gives it a hostname of Web 2, this might actually be the easiest way to communicate with it. Then we'll also want to know, hey, does it have SSL possibly? We'll want to know if we're going to put SSL in front of it, and if so, we'll want an SSL certificate. That certificate would probably be a big long string, something like cert, and then we could maybe add /n to delimit all the lines. String delimited. And search strings are something really not like that. But anyway. And then we also maybe want to tell it which Nginx to pick up on. We might have 5 or 6 or 8 different automated Nginx instances out there. And we don't want them all to load balance everything, so maybe we'll just tell this one Nginx prod is what we're going to register. And the last name, we might actually want to know the host name. We might want one Nginx load balancer to load balance multiple services, and depending on the host name coming in, direct it somewhere else, basically doing virtual hosts. So let's say we also might want to track a host name, and that would be called test.com. So host name, production, SSL cert, all these types of configurations can live in several places. They can live directly inside the service's code, and the service can know all that it needs to know about itself and automatically register itself there. Or they could live in environment variables, so another service can observe them and register those services. And that's the way I tend to like to do it, is to put all this information in environment variables. That way it's configurable and other services can read it and react to it. At any rate, these are what we need to capture. Let's move on and actually get some registration going. Now that we have our etcd registry going, registering a service from within an existing service is actually extremely easy to do. Here's our sample Node.js application that we've been using all along this course. It replies a simple hello there to every single request, so it's completely useless. However, adding registration is simple. We're just going to simply require the register file. The register file is going to use the etcd library that's available for Node.js, and pretty much every language has a good etcd API already built for it. And we're simply setting some options. We're going to set a TTL of 10, which is a lot shorter than we normally want it to be, but I don't want you waiting around for 30 or 60 seconds while we wait for the TTL to expire. So in 10 seconds, all of our registrations will expire, and then we're creating our new etcd, and the host is simply etcd. Since we can refer to it as etcd, since it's in Docker networking and we can use the host name. Then we're going to run this register function. Let me add a space there for clarity. We're going to run the register function, and every 5 seconds, we're going to re-register ourselves. Again, this is a lot faster than we'd normally want to, but it'll expire after 10 seconds, and we'll register with a heartbeat every 5 seconds. That way, it'll be on there, and it'll go away pretty quickly if for some reason this service dies. Then we're just going to register some of the information we've needed from before. We're going to set services web host to be test.com, services web port to be 3000. We're going to create the directory of services web upstream, and then we're going to add our hostname variable. So pretty much the only thing this service doesn't know about itself is what its specific hostname will be called. Will it be web 1, web 2, web 3? This will be created when the container is run, and it'll be different for each container. So all we have to do is set it as an environment variable at runtime, and we'll be good to go. So in this case, we're going to register our upstream as web1 if we run with an environment variable hostname of web1. That's it. It's extremely simple. We can build it, we can push it, which I've already done. I've built and pushed as willrstern/sample etcd register. So now we can go over to our Swarm Manager and run that. Now I'm also logged in on our other Swarm Manager terminal here, so I can actually curl etcd and see if any services exist. This is an Alpine Linux image with curl installed, and it's on the same network of apps, so I can real-time check etcd to make sure that the service registration has worked as it should. So let's go ahead first of all curl etcd. There we go, we have keys, and let's look at services. And let's add a recursive true. All we have is services. We have a services directory of keys, and nothing is on it. So let's go over to our Swarm Manager, and let's run our service that will auto-register itself. The name will be web1, and I also want to add that environment variable so it knows to register itself as available as web1. There we go, that's simple. Now the container can know that it's web1. And we're also going to add a constraint because we want to run this on the apps nodes. And there's my container name. And let's see, I think we have everything. Let's go ahead and run it. Okay, it's running now on a node. Let's start checking, and instantly you can see that we're registered. We're registered as web1, and you can see there's quite a bit of detail in there, so let's actually break this down. Let's go services, web. You can see there's our services web. Let's get a port. That'll be something a little more useful. Port value of 3000. So we've registered that. Let's see what our host name is. Did I call it host? Yep, host. Test.com. We've registered that. And let's see what our upstreams look like. Recursive equals true. and we have web 1 as an upstream. Excellent. Let's go ahead and run a second one. Let's go ahead and run a host name of web 2 and call that web 2. Okay, so now we have two webs running, one called web 1, one called web 2, the exact same container, and they're going to register themselves almost identically, except for they're going to call themselves a different upstream. So if you can read this messy JSON right now, you can see that we have a key called services web upstream web 1 and another one called services web upstream web 2. They've registered multiple upstreams now, and everything else will be identical. I can clear this out and go back to port. You can see the port is still 3000. We just have one port. They're working in harmony. They're doing excellent. Let's go ahead and shut one of these down. Actually, let's go ahead and shut them both down. Might as well remove them to keep my server clean. There we go. They're stopping and deleting right now. And we should be able to go check etcd here. And those values should be gone within a matter of 10 seconds. Okay, so the port's still there. I'm going to keep checking. And you can see the port is no longer found. Let's see if the upstream is there. The upstream directory is there. And there's absolutely no keys in the upstream. So this would get taken out of a load balancer at this point. So there's your basic in-service registration. It's extremely simple. Just connect to etcd and post that you exist with a TTL. If you go away, then your service will eventually get removed from etcd, and Nginx, who's polling or listening to etcd for changes, can automatically notice those changes. Here we have the code for a Sidekick service registration container. Now, what's different about a Sidekick service registration container is several things, actually. One, all the registration components are completely separate from the web application. So if your methods of registering and discovering services change, your web application itself doesn't have to change. That can be seen as an advantage. Now, the disadvantage would be that you have a separate piece of code that you have to maintain. Other advantages that you have is a separate container can be a little bit more introspective into the running container. For example, in this case, here's our Sidekick container, and as you can notice, the code's extremely similar to what we did when we were registering our service within our service. However, we're able to actually make HTTP requests to our service. This means that we're able to determine service health in a little bit more of a robust fashion. We can make sure that the HTTP server is running. We could also test to make sure that those requests come back within a specific allotted time frame. So we can not only check that it's up, but that it's running correctly and that it's running as efficiently as we want. We can also do some things like, if for any reason that HTTP request fails, we can catch it and immediately remove it from the service. That's not really important with a load balancer like Nginx, since Nginx handles that failover really well, but it's a possibility and it's something you can be aware of. So in this case, we're getting one configuration variable, and that's the container name, just like when we were self-registering. So we could make an HTTP request to that container. We already know it's on port 80, although we could make this a little bit more of a generic of a registration that could be configured with a port. It could also be configured with what host it is. There's a lot of things we could configure it with a service name, but in this case, we're keeping it simple. We already are pretending that this is a custom-built registrator for the service of web. So we know it's on port 80. We know it's called test.com. We know it's called web. All we need to know is what container are we monitoring with this instance. So there we go. I've gone ahead and built it and pushed it to Docker Hub as sample etcd Sidekick. So let's go ahead to our Swarm Manager and let's run some Hello World containers. I'm going to add a constraint of apps like usual. And I'm just going to run a sample Docker Cloud Hello World container. And then I'm going to go ahead and run a second one, Web 2. Now let's go ahead and verify that I haven't left any mess from before. Okay, you can see I actually do have a mess from before. So I'm going to go ahead and delete all my services web, just to make sure we're starting completely clean. So let's go ahead and do a git recursive on services, and we don't have anything. Okay, so the two web containers are running and they're not registered at all. Now let's go ahead and run that Sidekick container to look at it. So we're calling it Web1 register, although the name isn't really important. So what is important is we're going to add an affinity. The affinity is much like a constraint, except for it tells us we want to land next to the container called Web1. So this is going to do what it can. The manager will do its best to put this on the same node as Web1. This will make it more efficient. Now what we could actually do is we could make this affinity on the Nginx load balancer container if we wanted the registration to happen on there. So we could also make sure that the Nginx load balancer would be able to access it. That would help diagnose any possible networking issues. But usually I just set the affinity to run right next door on the exact same node. That way if the node goes down, the Sidekick goes down. If the node comes back up, the Sidekick comes back up. So the only thing I need to do at this point is I need to give it the container environment variable so it knows which container it's watching. There we go. We're watching Web1. That's quite a long command, but we're giving it the name of Web1 register. We're saying, hey, put me next door to Web1 if at all possible. And then we're going to watch Web1 and we're going to run that container. There we go. Let's go ahead and run it. It's running. And you can see that our service has already been registered. So now we can run a second one. This is the exact same command, except for we're going to watch Web2 and we're going to have an affinity towards Web2. And we also have to give it a unique name since I gave it a name of Web1 register. There we go. And now you can see that we've got a second upstream as well. We've got an upstream of Web2. So let's go ahead and just run a Docker PS just to see where everything landed. You can see that we've got a web register and we've got a Web1 register, and they're both running on app1 alongside of our Web1 and our Web2. Our app1 node caught Web1 and Web2, so the registers both ended there as well. So there you have it. That's how you run a basic Sidekick. So you can see it's a little bit more featureful, but in my opinion, the work added and the extra code maintenance usually doesn't make it worth it. I tend to like going with a self-registration process or an automatic, more generic registrator that does all the work for you. So far, I've covered the first two ways you can handle service registration. The first way being that a service registers itself. The second way would be that you run a Sidekick container that handles the registration portion. The third way would be to have an automatic registry container. Now that registry container would be aware of all the other Docker containers on its node. So when containers run, if they have the correct configuration, the registry container will register them. And when they stop or get destroyed, then the registry container would notice and it would automatically deregister them. So that's not really too complicated to do, and it's actually my preferred way. There's a slight disadvantage to it in that you actually have to code or configure the registry container if you don't code it yourself. There are several options out there, such as Registrator. But that little bit of extra work means you set up registration once, and then from then on out, you just have to add a little bit of configuration to your services to get them to automatically register. And so that little bit of work at the beginning tends to always pay off in the long run from my perspective. I'll show you how that works and how a container can be aware of the other containers running. Let's go ahead and SSH into one of these application nodes to show you how that works. Okay, there we go. We're into that node and I can run Docker PS. You can see that I have one swarm image running. We want to give Docker privileges to a container running on this node. And we do that by mounting the Docker socket. If I look at the var run folder, I have the Docker socket. And that's what the Docker CLI connects to and what gives it privileges to run containers. So if we mount that Docker socket into a container, then we've essentially given it Docker daemon privileges. So let's go ahead and run an Ubuntu container and mount that Docker socket. And I'm just going to log in with a bash prompt. So there we go. I'm now in an Ubuntu container. Let's go ahead and install docker.io. I made a mistake there. I forgot an L on my install. So there we go. 2 L's, install. So Docker's been installed. I can now clear that screen and run Docker PS. Again, I'm in an Ubuntu container right now, and you can see that now it shows two images, Swarm and Ubuntu. So I've essentially granted a root level access container, my Ubuntu container, privileges to Docker. So it's extremely important to note right here that anytime a container asks for that var run docker sock volume, you're giving it root level privileges. You should really know who that container is coded by and what that container is supposed to be doing before you ever grant those permissions, because that's very powerful permissions. So our Ubuntu container has those permissions. We can go ahead and exit out now. And there's a few things we're going to want to do to get this automated service registration going. First, we're going to want to run services with some configuration detail about themselves. They don't have to have much, but that container is not going to know everything on its own. It's going to need to know a little bit about each service. Secondly, we have that service registration container. That's going to look for all the services that match that configuration. If a service has correct configuration, it's going to register it to etcd automatically. And if a container doesn't have proper configuration, maybe because it's not a service, maybe because it's something else that's running on that machine, it will ignore it altogether. Here's what I mean by some configuration. It's really not that much, and we're going to add it via environment variables. A container is going to need to have a service name. Let's say we have Web 1, Web 2, and Web 3. Those all belong to the web service. And the registration container really won't know that unless we label it. So there we go, we're going to add the service name environment variable. We're also going to add a virtual host environment variable. We're going to add a tag, maybe Nginx's production. Maybe this will be a part of an automatic Nginx service. So Nginx will automatically reload any services out there. We don't want every Nginx container to reload every single service out there. So we're just going to have the one called production pick up on this and serve traffic to it. And then we're also going to look to port 80. That way we know that if we're exposing multiple ports, the port that our service is on is port 80. So if we have these 4 tags, then we should have everything we need to register the service properly. Let's go ahead and look at the terminal commands sh from our working files. And we're going to go ahead and run a hello world container with these tags. You can see that I'm calling it web 1, running on net apps. I'm adding a constraint so it runs only on the apps nodes. And then I'm adding those exact environment variables we just said there. So I'm going to copy and paste that. I'm going to go over to my Swarm Manager where I'm logged in, and I'm going to go ahead and run it. There we go, it ran. And if I run Docker PS, you can see that I've got it running right there. It's running on apps 1. So now let's go ahead and run an automatic service registration container. And I've already created one for you. It's pretty simple. And I included this in the working files, and I'm just barely going to touch the code because you don't need to know Node.js to work with this. Almost any type of language will have a CLI type of interface for Docker. In this case, we're using Dockerode, which is an NPM package, and we're also using etcd to connect to etcd. So all this auto register Docker watch container is going to do is it's going to connect to etcd, and it's connect to Docker via that Docker sock that we already mounted, if you'll remember. And then it's going to look at all containers, and it's going to get some information out of those container configurations. We're going to get these environment variables, the ones we've already posted before. And it's going to skip them if that's not set. And assuming all the information's set and looks good, it's going to register it. So I was able to write this code in maybe an hour, maybe a little less, maybe a little more. But now I have automated service registration across all of my nodes if I want it. I'm sure there's some room for improvement in this code, but it's doing the job just fine so far. So let's go ahead and run this container that I've created. You can see I've called it Docker Swarm Registrator. We're also going to run it on apps, and we're also going to give it a negative affinity. We're going to call it register1, and we don't want it to run next to anything else with a container that starts with the name register. That way, when we run 2 of them, it will run on the 2 different app nodes. So I'm going to run this command once, and I'm going to run this exact command. I'm going to call it register2, and this negative affinity means it will not run on the same node as register1. That way, we're going to have 2 registration containers running on 2 app nodes. Let's go ahead and run that command. There's command 1, there's command 2. So if I run Docker PS now, you can see that I've got register1 running on app 0, register2 running on app 1. So now if I were to go ahead, I'm on this Alpine node over here. Let's go ahead and check out etcd. You can see that we've got services that are automatically registered. I'm going to go ahead and grab this so you can see what that giant blob of JSON looks like. Let's go ahead and clean this up. There we go. You can see that we've set services web hosts has test.com. and it's got one upstream. It's saying the upstream is web 180. So we could go ahead and curl web 180 and it'd be just fine. You notice that in my Docker watch, if I look into that code that I've presented to you guys, I'm grabbing the host name. Since I'm using Swarm host names, I figure it's just as simple to use the host name as it would be to use the IP address. Instead of doing that, I'm simply calling it web 180. So there we go, it's registered. Now we can run some more commands. Let's go ahead and run multiple more instances of web 2 and web 3. I'll copy those commands again out of my working files. Now we're running web 2, now we're running web 3. And if I do the exact same command, hey, give me all the services from etcd, you notice this blob has grown. Let's go ahead and look at it again. Let's copy and paste it in here. There we are. And pretty that JSON up. So now if I were to look at my test.com upstreams, I have two upstreams. I have web 180, web 280. Oh, and my mistake, we actually have 3 web upstreams because I ran 2 more. So there we go. Now our Nginx could load balance between all 3 of these. What's great about this setup is I don't just have to register web services. I can register all the services I run. So let's go ahead and run another one. And let's say this one's called API1. And let's say it has a virtual host of api.com and the service name is API. Essentially, it's a completely different service. If we run a completely different service somewhere on our apps nodes, that will also get automatically registered immediately. So there we go. I can automatically check that etcd services, and that giant JSON blob has grown even more. Now, if I were to paste it and prettify it, you can see I not only have a services of web, I also have a services called API. Services API. API has its own upstream now with API port 80. So no matter how many services I run, they're automatically going to get registered, automatically going to get deregistered when they come away. And that can totally be up to you. How fast or how slow you want it to happen can all depend on how you code that auto register container. And again, there's a great container out there called Registrator. It has its limitations, but it also has its situations where it works very well. And that's how you'd handle automated service registration. If I run Docker PS on my Swarm right now, here's what we have going on. We have an API container, which is really just a hello world container. And then we have 3 web nodes, web 3, web 2, and web 1. Then we also have our auto register containers, register 1 and register 2, one for each node. And they're auto registering all these containers to etcd. So the only thing we need to wrap up our service registration and service discovery workflow is a load balancer that picks up on all these things getting registered to etcd. And if you use an existing container, that's often very simple. I have an existing container that I want to show you here, so we'll show you how that works. Let's go to the working files. The container is called Nginx etcd. It does 2 things. It runs an Nginx server, and then it also runs a Node.js process in the background to check etcd periodically. Whenever the configuration has changed, it templates out a new configuration file for Nginx. It tests that configuration file, and if it tests successfully, then it reloads Nginx, and all the new configuration starts flowing without any downtime. It works very well. So let's go ahead and copy this command. We're going to run it on the network of apps, give it a name of load balancer 1, and for the first time ever, we're going to expose a port publicly. Port 80 is going to be exposed, because after all, we want to actually receive traffic to this load balancer. We're going to do the same thing we did with the auto registers. We're going to give it an inverted affinity, a negative affinity, so it's not going to run next to another load balancer. And then we're also going to give it a constraint of type load balancer, so it ends up on the load balancer nodes. Lastly, we're going to give it an Nginx name of production, which is critical for this container because if you remember when we registered our services, we told them to register to the service of Nginx name production. So this way it will pick up on anything with a registered Nginx name production. So there we go. Let's copy this and run it. I'm logged into the Swarm Manager now. There we go. I've ran the first one. Now let's go ahead and copy the command and run the second one. The second one is essentially the same command. We're just calling it lb2. And with that negative affinity, you'll see on the next Docker PS that they ran on different nodes. You can see we have Swarm lb0 and Swarm lb1. So now all we have to do is check out our applications. If you'll remember when we registered them to etcd, we registered our API as responding to api.com, and we registered our web nodes as responding to test.com. So we can test these out pretty easily with a curl command. We can simply run curl, and let me snatch that IP address real quick. Let's choose LB0. We can spoof a host as if it came from a DNS of test.com, and we can paste in our IP address. The host name of test.com is exactly what will happen if test.com points to this IP address. And there you go, we're receiving hello world. Now you'll see this hello world spits out that as a host name of 2389. If I were to hit that exact thing again, I get a different host name. It's successfully load balancing my different web containers. 039A. I have a third one. So right about now, it should start coming back to 2389. You can see it's doing the default round robin, 79BA, 039A, and then back to 2389. So that command is load balancing between all of my containers. Let's change it up now and change this to api.com. So we have a completely new domain name. We're pointing it to the same LB nodes. And there we go. We have a new host name, 33D8. So it's excellently working with any of our containers. They're automatically sending traffic to the right place. Service registration and discovery, once you go through the little bit of pain to get it going in an automated fashion, is extremely simple. Now, if we want to see this in a web browser, we simply have to update our etc hosts file on our computer. Now, I can't really show you my etc hosts file because I have some sensitive information in there, but essentially I'm just going to edit it with sudo sublime etc hosts, and then I'm going to add two entries. I'm going to add an entry for this IP address, will be test.com, as well as api.com. So I'm going to go ahead and add that now off screen, and we'll be back to check it out. Okay, I've gone ahead and added it. Let's go to our browser and open up a new window. Let's hit api.com, and there's our hello world. If I refresh and refresh and refresh, I continue to get the same host name. Now let's change that to test.com. There we go, we're getting 79BA. And if I continue to refresh, I'll get a whole bunch of different ones in random order. Excellent, so our dynamic service discovery is working very well. At this point, the only thing to do is set up true DNS to point to this. And also, since we're running it on two nodes, LB1 and LB0, we can set up a dynamic DNS like DynDNS has with failover. So if our LB0 goes down for whatever reason, be it the container or be it the actual physical node itself, within moments, DNS will flip over to this node and traffic will keep flowing without interruption. You can also at that point get a monitor that one of your load balancers has gone down and DNS had to flip over. So it's a good setup to use. Again, automatic service discovery is one of the gotchas with using Docker, but it really helps and it makes it extremely useful to scale and move forward once you get it set up. Let's say that API starts getting really slow with its response time and we want to scale it up. That's very simple to do. Let's go back to our working files. We're going to run the exact same command to run our API2 container. You can notice it's the exact same command as when we ran our API1 container. We've simply changed the name to API2. Let's go ahead and copy that and run it on the Swarm Manager. There we go, API2 is running. And now back to our hello world. API.com should now be load balancing between two containers. Yep, 33D8 and 3AD6. So scaling is that simple and that fast once you get service registration up and running, and it really makes Docker a lot of fun at that point. For those of you guys who watched the last video and felt like that Nginx etcd container was a little bit magical, I want to step you through the code that I used to build that, just so you're aware of what all it entails, in case you wanted to rebuild it in another language or implement something like it in your company. So all the code is on GitHub and it's public, but I'll walk you through really quickly what the minimum requirements are. So first off, I'm starting with this Docker file, and I'm picking from Ubuntu because I want to use bash for the command that I run. And I'm installing Nginx and Node.js, since again, Node.js is the front-end watcher process that I'm using here. And then I simply run Docker Cloud Watch, which is a bash script. So here's that bash script right here. I'm starting off with pipe fail, which means that any errors are going to bubble up really nicely. And then I'm going to start Nginx and start that node process. That's really it. And then I'm also going to take any Nginx logs and include those in the standard out. So the standard out logs will include any logs from the node process and any logs from the Nginx process. That also is really important because if either of these processes has problems or information to show, you want to be able to see them from Docker logs. So that node Docker Cloud Watch is just doing four things. It's watching etcd. On changes, it's making a new config file, which it's doing from a template. And then it also tests that out with nginx. That makes sure the config is actually going to work. If that config passes, then it reloads nginx and starts using that new config file. Here's that config file. It's essentially a very simple nginx config file. It starts off with a default route, and then it also has a status page for stats such as Datadog. And then here's what actually gets used for all the new services. It includes any upstreams for your host, and then it includes your host name there, and then it automatically routes to your upstream name. Now, if you want to include SSL, which we'll get into in a little bit, it gets a little bit more complicated, but not much more. That's really as complicated as your nginx template has to look if you want it to support all of the sites that could potentially be load balanced. Let's look real quick at this Docker Cloud Watch.js, the Node.js process. We're really just loading an etcd watch and a reload nginx. And then we're going to start off by getting those services, and we're going to continue getting all those services from etcd every 5 seconds. Now, this is a really, really fast process. It really could run every 1 second if we wanted it to without causing any kind of performance hit. But if you had any concerns, you could easily run it every 10, 30, or 60 seconds. So that's really what's going on. It's extremely simple. It took me a little bit to figure out the first time I had to code it, but once I figured out how to do a watcher and reloader like this, it's really not a lot of work, and it's reusable across as many apps as you want to. So it's a great thing to get the experience building.
Once I have dynamic load balancing in place, it becomes pretty easy to also add SSL for secure traffic. So here I have a self-signed certificate that I've generated for test.com. So I will get that annoying security warning, but it'll definitely work just fine. I can begin by taking this key and converting it into one long string, and then I can actually paste it in as an environment variable, the same as the rest of the configuration for my service. So I'm just going to do a quick find and replace, and I'm going to go ahead and replace any /n's, which is new lines, with an escaped /n. So here we go. You can see it just became a one-line file now. One gigantic string with /n instead of any line breaks. So I'm going to copy and paste that. And now I can add a new environment variable with that certificate. There we go. And I'm going to want to also wrap this in some single quotes so it doesn't deal with escaping or any kind of strange issues. So there's my service certificates. And now I can run this, and the Docker dynamic nginx container will pick up on this and do two things. One, it'll take this search string out, and then it'll replace those /n's with real line breaks, and it'll write the certificate file. And then it'll also create an SSL template for the SSL traffic to come through on port 443. So everything should still work just as we expect it to, and we should be able to serve SSL traffic now. Let's go over. I've already stopped my web1 container, so I can just run this big old command. Wow, that's a long string. As you can see, that certificate is pretty long. And you also notice I've included the private key in with the certificate because nginx can use those in the same file. So that's helpful as well. So let's go ahead and run that. That's running. Let's go check out test.com. Okay, test.com is working, and let's try HTTPS. Connection is not private. Well, that works. This is pretty much what I expected to see. Proceed to test.com. And there we go. I'm getting the red X, but I am getting HTTPS with my self-signed certificate. So as you can see, it's pretty much just as easy to do SSL termination and send in all the SSL traffic. What's also nice about this is since nginx is handling the SSL termination, my actual application, my Hello World application in this case, doesn't have to be concerned at all with SSL traffic. So that's really a good pattern with doing things. SSL termination, offloading that to nginx, and then keeping the application simply the application. If I'll go back to my command here, it's also useful to mention that these environment variable configurations that I'm setting don't have to live in the runtime command. These can easily live in the Docker file, and there are some advantages and disadvantages either way. If we put these in the Docker file, then the configuration for the service gets to live right next to the code for that service itself. So that's kind of useful. The disadvantage is to push out a configuration change, I have to push out a code change, which has to go through continuous build and deployment. So it's a little bit slower to get configuration changes out should there be a fire scenario going on.
If I do put these in runtime, it's a much more convoluted command to run. As you can see, I could easily keep this command on one line if I got rid of all these big service environment variables. However, if I want to make a change, I can simply stop a container, modify that runtime command, and restart it. So depending on your circumstance, you may want to put this configuration in a runtime command or in a Docker file. It's really up to you. Either way, a few environment variable changes, and now our test.com service has SSL termination and everything's continuing to work very well. Let's take a moment to talk about some Docker anti-patterns. These are some things that you'll want to stay away from in your Docker coding journey. And if you stay away from them, they'll save you a lot of headaches and a lot of confusion as you're building out your applications and scaling them in the beautiful Docker way. So let's begin. The first one is you want to avoid using the latest tag. This will also happen if you don't include a tag at all. If you run a container, say docker cloud/hello world, by default, that's going to give it the latest tag. What's bad about this is you really don't have a lot of control over what version that latest version might be. So it's always a good idea to specify a specific version. At the very least, specify a major and minor version, but I'd encourage you to always specify a major, minor, and patch version, because not every developer understands semantic versioning. 2.1, if it were to upgrade to 2.2, should include new features but no breaking changes. Breaking changes should always result in a 3.0. Not every developer understands this, and all the time, people will upgrade 2.1 to 2.2 and introduce breaking changes. So it's always a good idea to specify the version that you're going to be running. And if you're building a Docker file in the from tag, you want to also include the specific version that you're building from. And lastly, when you're ready to push your containers into production, it's a good idea to check the upstream images that you're building from and make sure that they're not using any latest tags or lack of versioning tags as well, because you want to make sure that your upstream won't break on you. As long as you're set up right, but your upstream is set up wrong, you're still essentially set up wrong. So you'll want to check the upstream images that you're using and see if they're using any upstream images as well. And if you have to, go all the way up the chain to make sure there's no latest tags being used. It's a really good practice, and it can save you a lot of problems during your builds and might even save you some downtime along the way. Okay, next up, you'll want to avoid running multiple processes in one container. As a general rule, you want a container to do one thing and do it very well. Now, you're totally legally allowed to run multiple processes in one Docker container. Some of the disadvantages that you run into is the fails and restarts are simply not as clean. What if one of those processes fails, but the other one still runs? Well, how do you actually know that that one has failed? It can be a lot tougher to troubleshoot your code. It can be a lot tougher to make sure the logs and everything are completely accurate. Also, monitoring is a lot more accurate when containers are just doing one thing. If that one thing goes down, you know that it goes down. Whereas if one part of a container goes down, it's really hard to have a monitoring event on that. Whereas if you have two services and they're simply running as two containers, it's so much easier to monitor those by name, and many services out of the box have a lot of features that allow you to monitor container uptime by name. So those are two very good reasons for running as many broken apart processes as possible. Also, there just aren't very many truly necessary use cases for running multiple processes. About the only one I've run into so far is when you have something like a dynamic load balancer that also needs to have a process that watches its service registry. That's a use case that's very helpful, but besides that, there's not really any that I've run into. Next up, you're going to want to avoid statically published ports. Statically published port being, I'm going to run this container and I'm going to have it expose port 3000 as whatever it wants to expose it as, 2378 or something like that. In general, you're going to want container communication to happen without statically published ports. They should be able to talk via hostname networking or direct IP access to each other. For several reasons, really, there are some security concerns that have to be addressed and thought about when you're publishing ports. Whereas if you're not publishing ports at all, there's really no security concerns to deal with. Just lock down all ports. No one can access any of them because we're never planning on publishing any ports. If you're not publishing port 443 or port 80, you need to ask yourself, do I really need this port published?
Does this port really have to be the way that this container receives communication? Or is there a better way? A way that allows me to lock down much more traffic in a big block and not have to worry about any access being granted. Also, you have to ask yourself, is this just an improper setup? Is it that I can't see the container that I'm wanting to talk to, so I find myself wanting to expose a port so then I can talk to it? Maybe you need to go through a little bit more setup on your Docker Swarm network or on some of your other networking components so you have easy hostname access to different containers. Lots of times, if the setup process isn't gone through correctly, it's really tough to get inter-container communication working without exposing these ports. So make sure that you take the time setting up your actual node cluster correctly so you can run containers the way you really want to run them and lock down security the way you really want to lock it down. Manual deployments are the next thing you're going to want to avoid. And lots of companies always stay away from manual deployments, but lots of companies do manual deployments. I will throw out to you for your consideration that manual deployments almost always cost more time than they save. If you take the time to automate things well, not only will you save time in the long run, you'll also end up with a drastically more repeatable process, and there will be a lot less human error in that equation. Take the time to automate things well. You'll never regret it. Also, with Docker, continuous deployment can be significantly less complex than many other ecosystems. It may seem like continuous deployment is going to be a difficult journey, but if you're using Docker and haven't been able to get it working with other technologies, give it a try again. Revisit continuous deployment. It's probably not as difficult as you think it'll be. Lastly, deployment dependencies are a big anti-pattern. You want to avoid as much orchestration as possible. Another way to word this would be, services should all be able to deploy independently. You'll save yourself a lot of headaches if you can deploy a service at any point in time without needing all the other services to deploy along with it. You should avoid orchestration at all costs. Orchestration at first seems really cool that you can deploy a lot of containers in harmony all at once, but in real life, in code, we often want to change just one container and get that fix out there. You don't want to have to wait on everything else to be ready to deploy along with it. You really want individual services to be able to deploy individually. Also, you want to code for downtime. A service should be able to start in any order. And if its dependent services aren't running, it should be able to connect to those when they are running. This will not only make your deployments easier, since you can deploy things in any order, but it'll also make your uptime better. Whereas if a service goes down and it comes back up, your dependent services are able to recognize it when it comes back up and everything moves forward as normal. So there you go. There's a few anti-patterns and things you'll want to stay away from as you're coding with Docker. Stay away from these things and you'll avoid a lot of headaches, and your journey will just be a lot more fun as you get into this great new technology. We're going to go ahead and build a rolling deployment for deploying multiple containers continuously across a Docker swarm. It's a little bit different, but it's essentially the same as how we do continuous deployment for one container. There's just a few adjustments we have to do to make it work really well with Docker Swarm. So I have this very simple Hello World application, and it's currently running as Web 1. I can reference it on my machine by curling test.com. There you go, test.com returns Hello World. So let's go ahead and run this deployment, and I'll show you the continuous deployment script I have right now for running the one container strategy. It should look pretty familiar. I'm doing a build and a push, and then I'm logging into my Docker Swarm manager, and I'm doing a pull, a stop, a remove, and a rerun. And all this will happen really quickly. Let's go ahead and run this deployment, and I'll show you a few weaknesses to this strategy. So as that's running, I'm going to run siege against test.com, which will make continual requests so we can see if there's any downtime. You can see that the requests are pouring through one after another, one after another. I believe there's 15 users by default going on. And right about the time we do a stop and restart, we'll see just a little bit of downtime. Yep, there it was. We missed about 6 requests. Now, that was really fast for a couple reasons. First off, Docker does restart containers extremely fast because they're not virtual machines. It can stop one and restart another one almost instantly. And also, we're doing that pull, the heavy lifting, the time that might actually have some network latency to it, in advance. So once the pull's done, then we're going to do stop, remove, and restart.
So that's very fast, and also, Hello World doesn't take any time at all to start. It essentially starts instantly. But that downtime is something we'll want to avoid. In a real world situation, the downtime will be just a little bit bigger, as most applications don't start quite that fast, and also we'll want the ability to scale if our traffic ever grows to our application. So let's get into scaling this to a multiple container deployment and still keep that beautiful continuous deployment aspect. I want to point out one more thing we need to address. If you'll notice when we did that Docker pull, it did a pull on every single node across our entire swarm. That means the load balancer nodes did a pull of this test node as well as all the app nodes, whether it's running on them or not. This is a limitation to Docker Swarm, and while I believe they're working on an ability to specify a specific node, they don't have it in there quite yet. But there's a workaround we can do by building a container on a specific node, and then it'll automatically run on that node with the container we've built. So let's go ahead and look at this script we're running here for our deployment, and instead of doing a Docker pull, let's do a Docker build from this container. Now, one of the great things about build is we have the ability to specify build arguments where we can post some constraints. So I can go build arg, and I can add an affinity in here. So there we go. We're going to run this build on the node that has web 1. And I'm also adding a tilde there in case this is our first deployment, web 1 won't exist. I don't want it to fail. And we can also make that build force a pull because we always want to pull our latest. And then what I can do here is I can pipe in a brand new Docker file. And I'm just going to say from will stern test node. So what I've essentially done by doing these triple less than symbols is I've created a brand new Docker file right here, and I'm piping it into the standard in to this Docker build command. So it's building from my brand new Docker file that only has from will stern test node. And then I'm going to build it on the web 1 container. So we're essentially doing a Docker pull to only one node. So then we're going to stop web 1, remove web 1, and start web 1, and everything will work just fine. We just won't get that Docker pull across every node. So let's go ahead and make a change to server.js and try this out. Let's go, instead of saying hello world, let's say hi there. Save that, run deploy sh, and I'm going to watch this time instead of siege. So we see hello world. I'm curling every 0.2 seconds. Hello world, and soon here we'll see hi there. There we go, a little bit of downtime, and we have hi there. So there, it worked successfully, and you'll notice over here, it did a build and a pull on one node only. It didn't do a pull on every single node, and our deployment still worked just fine. So now all we have to do to scale to zero downtime deployments is move from deploying one container to deploying multiple containers. And we do that by doing exactly what we're doing now. We simply run a for loop. So from 1 to 3, we're going to be running 3 containers. We're going to do what's inside this loop. And now all we have to do is, instead of explicitly setting web 1, we're going to set web $I. So that's going to be web 1 the first time around, web 2 the second time around, web 3 the third time around, and so on and so forth, as big as that loop is. Let's go ahead and run that deployment again, but first let's change this to, I don't know, let's say hola. There we go. And again, I'm going to run siege here so we can see if there's any downtime this time around. There actually should be downtime this first time around because we're stopping web 1 and there's no other web 2 and web 3 to take its place. So this first deployment, we should still see that little bit of downtime, and then after that, we'll see 0 downtime as we redeploy. There's that familiar level of downtime. And then we're saying there's no container web 3, no container web 2, but it's all running still just fine. Let's go and do another redeploy. The pulls will be a little bit faster this time since there's no changes to what we're already doing. We're stopping web 1, and the traffic's still coming through just fine. Now we're stopping web 2, still no dropped requests, and web 3 at this point we can be confident will also stop and restart with no down traffic. There you go. We just did a 0 downtime deployment, and let's go and see what happens as we watch this. So every 0.2 seconds, I'm going to curl test.com. There's hola. Let's go ahead and change this back to hello world and run that deployment one last time. So what we should see here is we should start seeing hola and hello world at the same time as we have the newer containers coming in and the old containers going out. There we go. It's going back and forth from hola to hello world. And soon we should just see only hello world. There you are, and now we're pretty much just seeing hello world. So as you can see, we had a couple little obstacles to overcome. With about 15 lines of code, we're able to get continuous deployment going with a rolling deploy strategy in almost no time. The next deployment strategy we're going to look at is called a red-black deployment. Let's go ahead and look with a visual illustration of what this is. So say you're running your current version of your application. It's one box shown here, but that box represents all the containers. Let's say 3 for this example. Next up, you're going to keep current, and you're going to deploy the new application, the new version, right alongside of it. So now we have our 3 current running and our 3 new running. This way, traffic is shared between the two. If we start seeing any kind of error, we can destroy those new ones and the current keeps running. So rollbacks are very, very fast with a red-black deployment strategy. Also, the red-black strategy allows us to scale traffic onto the new. If the new was uncertain and we weren't really sure what was going to happen, we could start by just running one new container, and essentially a quarter of the traffic would now be coming to our new container. Then we could watch key metrics and see if they go up or down. If they take a sharp turn to the wrong way, we can kill that new container, and if they fix themselves, we know that that new container, that new version, was problematic. If not, we can move forward. We can add 2 or 3. If we trust that new version, we could also deploy all 3 at once and watch those key metrics and do a quick rollback if it doesn't work. Regardless of how we do it, we're allowed to run both of them side by side, and it's not quite as catastrophic if things go wrong. Next up, we say that we like the new version. We go ahead and we kill the current version. All traffic is coming to the new version, and lastly, the new version becomes the current version, and we're ready for the next deployment to begin. So as far as why you would do this strategy, aside from what I already mentioned, you might want to choose this strategy if you have an application that takes a while to start up, which you shouldn't have with a Docker container, but sometimes you simply can't avoid it. There's bootstrapping processes that just have to happen. This allows you to start up that new and wait a little while before destroying the current one. Also, as I said, it's great for scaling traffic onto multiple versions of an application, and it makes rollbacks extremely fast and easy. So let's get into how you would code this with continuous deployment. And continuous deployment isn't always the solution, but it'll show you how you do it if you would stage it as well. So here we are with the rolling deployment script. And we just have to make a couple changes to do a red-black deployment, again, assuming we want to do a continuous deployment strategy. Now, lots of those advantages you get that I mentioned before, you don't really get if you do it with a continuous deployment strategy, which is why it's more suited for things that you don't want to deploy always all the time. Rolling deployment generally makes more sense for that. But again, if you can see it here in code for continuous deployment, it'll make sense on how you would do it if you were to stage it. So first off, we want to go ahead and do the build exactly as we're doing right now. And then we want to move this stop and this remove down for later. I'm just going to move it down here and comment it out. So I want to keep that Docker run, but what I want to do is I want to add an affinity to it so it runs right next door to Web 1. So I'm going to go ahead and add an affinity here. There we go. Now it's going to run next to Web 1, or if it's Web 2, it's going to run right next to Web 2. But then I can't give it the same name, so I'm going to call this new. So now we're going to have Web 1, and right next door, we're going to have Web 1 new running. So that way, the restarts are going to happen whenever we do kill web, automatically Web 1 new is going to take its place. This might not be the strategy you choose to do if your node cannot handle 2 instances of your container at once. But I know in this case that my nodes can all handle plenty of capacity, so I'll have no issue running 2 copies next to each other. So then I just want to make a second for loop, assuming I'm going to also remove the old ones once this is done. Let's go ahead and copy and paste this. If we want to automatically close out the old version right away, we can do that in another for loop here. We're going to automatically stop Web 1, remove Web 1, and then we're also going to rename Web 1 new to Web 1. There you have it. So that's what our deployment looks like if we're doing a red-black deployment strategy. Now, if it was the scenario where application takes a while to load, we know that it might take 20 seconds. We could sleep for 20 seconds in between the roll-up,
and the roll out of the current version. You could also do this manually, and it doesn't have to happen with continuous deployment, as red-black deployments are often what you do in a scenario where you can't quite pull off continuous deployment. But anyway, that's how you'd run it. The affinity takes care of making sure that the application runs in the same place every time, which may or may not be something you want to do. And then you also can remove it as a second step. So that's red-black deployments. The next deployment strategy that we'll look at is called a blue-green deployment. It offers some really unique capabilities, and it also makes for the easiest rollbacks of all the deployment strategies. So it's a really good one to implement if you have a high degree of uncertainty in the next deployment that you're doing. It also tends to work best when you're not using continuous deployment. Let's get into a visual illustration of blue-green. The concept behind blue-green is simple. Your current is blue or green, and then your next is going to be the other color. So if you're running blue right now, you'd go ahead and deploy a green version. Now the green version is getting no traffic. And how this works is the service registry will have a color switch for which color we're currently load balancing. So in this case at the very top, you can see that the web color is blue, so the router will only load blue versions. You could handle this color discernment in two places. The service registry could be smart enough to only register blue services at this point, but you also wouldn't be able to check those green versions. Or the router, the load balancer, the Nginx or HA proxy instance, could be smart enough to check the registry and choose to only pick the upstreams of the color that's currently set. However you choose to handle it, it basically will work the same way. We're currently running blue, it's receiving live traffic, and we're able to run a full version of green. While this green is up, we're able to run tests against it, we're able to preview it, whatever we want to do to verify that green should be what we want, and then we simply flip a switch in the service registry to green. As soon as that happens, the router picks up on that and starts funneling traffic to the green version. What's great about this strategy, and the biggest advantage it provides by far, is near instantaneous rollbacks. We still have the blue version up and running, so if there's any issues at all, we simply roll back to blue. We switch that toggle and blue flips back. We can redeploy a new green version, destroy the old green containers, put some new ones up there, toggle green again, and instantly the traffic can go back. And then when we're satisfied with the green version, we destroy the blue version and green is our current. So our next deployment begins by blue. And then the same thing goes back and forth on and on. Let's look at how this works in a real example. If you take a look at the working files for this lesson, I've included all the scripts necessary to throw a quick blue-green example together. We've got this basic web server, which you should be familiar with. Let's call it green deployment right now. Instead of saying hello world, we're going to say green deployment. So let's go ahead and build that web container. We'll just call it web. There we go, that built very quickly. And now we can run our registration pieces. And these should look familiar at this point. We're going to run an etcd registry on the net of apps. And then we're also going to run an automatic register container. Now this automatic register container varies a little bit from the one before in that it registers upstreams with a color. So instead of doing web upstream and then all the upstreams go there, it will look for a service color, which we are including right here. An environment variable with service color equals green will be added to the upstream green folder. And then if it's blue, it will be added to the upstream blue folder. So that's what's different about this registry that I built. I just made a tiny little code tweak and registered them by color. So I can go ahead and run these two containers right now. There we go, etcd's running and the registry's running. And now I can go ahead and use a curl container to do a single curl put command. This appropriate curl container is basically an image with just curl installed. So I can do a curl put to etcd, and I'm going to add web color as a value of green. So let's go ahead and run this command, and now the web color value will be green. All right, so everything's set up to run the green. So now I can run a load balancer. This is a blue-green load balancer that essentially does the exact same thing that Nginx does, except for it will pull whichever is set. So if the value is set to green, it will load green upstreams. If the value is set to blue, it will load blue upstreams. There we go, our load balancer is running. And now we can run two web green containers, and we should be able to see our example working just fine. And they're running as test.com, and I'm doing all this locally on my local host. So in my etc host file, I have test.com pointing to localhost. I should be able to run to test.com and see my example working. There we go, we have green deployment. So now let's go ahead and say we're working on version 2 of our app.
we're going to make some big code changes, and we're going to call this blue deployment. There we go, our blue deployment's run. Let's go ahead and rebuild this container. And let's go ahead and deploy some blue nodes now. It's the exact same command. We're just calling it web1 blue and web2 blue. And then we're also saying the service color is blue. So it'll get registered as blue services. Let's go ahead and run these two blue containers. They're running, and if I do a Docker PS, you can see that I have my 4 web instances running. Web 1 and 2 blue, web 1 and 2 green. And I'm also running the load balancer, the register, and the etcd. So let's go back and run test.com. You can see it's still just the green deployment. So to make this switch, all I have to do is do that curl command to re-put the web color to be blue this time. So let's go ahead and change this web color to be blue. Head over, and within seconds, I have a blue deployment. Nginx picked up on it, and now it's load balancing all those blue containers. Now, if there was a fire, oh my goodness, we made a big mistake. It's not doing what it should be doing. We simply rerun that command, and we're changing our value to green. And then all those running green containers with all their caching or whatever it is that they're doing has stayed exactly in its intact state. We're able to fall back instantly. So that's a great feature if we want to do any kind of uncertain deployments. We think it'll work, we're reasonably sure it'll work, but there's a lot of potentially breaking changes in there. A blue-green deployment is a really good strategy in lots of these cases, where even though you've tested it, it might take a little bit of live traffic to really prove that it's a good deployment. We can toggle back to blue now. Let's say we fixed it. The traffic's all blue, and we can go ahead and delete those remaining green containers. Let's go ahead and stop green and remove green. And there we go. Our next deployment will simply be called green. So that's kind of how a blue-green deployment works. As you can see, it's not really set up as much for continuous deployment, although if you did want to orchestrate multiple services together and wanted to really make sure that everything was spun up correctly, you could do a continuous deployment blue-green strategy, although I think rolling deployments still make the most sense in that scenario. But blue-green is great for when you have large release cycles and a high level of uncertainty. It gives you great instantaneous fallbacks, and it still works extremely well across the Docker ecosystem. If you're building an application with an external client, whether that external client is an end user to your website or is another team on your organization, and you have to do versioning of any kind, a multiple running version deployment might actually be a great solution for you as well. So here's how that strategy works. You essentially run multiple containers for each version that you support. If you have V1 and you're still supporting that, you keep the V1 containers running and simply launch new V2 containers. And then you could do something such as put Nginx in front of it and have the path of /v1 go to V1 containers, the path of /v2 go to V2 containers. This gives you the flexibility to completely start over for V2 using brand new technologies, a completely new stack if you want, and you don't even have to worry about V1 support, and it can be a very good pattern. Also, you could have your API docs be their own containers, so /docs can route to your API docs, and that can be a separate project that's maybe more in tune with the line of a front-end skill set, so even different people can work on that team. And then, obviously, if you want to upgrade to API version 2.1, you don't affect version 1 files at all. The containers keep running, no deployment is necessary, and absolutely nothing changed. So you have a high level of certainty that V1 won't see any regressions unless maybe you're messing with your database along version 2. So as always, let's show you how this works in real life. So here we are in the working files directory, and I've got those two familiar, extremely simple servers. I have API v1, which is simply saying API v1, and API v2, which is simply saying API v2. Then I also have this API conf. And what this is going to do is take anything with /v1, so api.com/v1, will route to an API v1 container. Or this could proxy pass to an upstream and load balance multiple API v1 containers. And then same thing, anything /v2 will go to v2 containers. And this will work excellent. So let's go ahead and go to our terminal, build these containers and run them. I'm just going to tag it as API v1 since I don't have to deploy it anywhere. And tagging API v2 as v2. Let's go ahead and run them. There you have it. My API v1 and v2 containers are running. So now I can send traffic to these two containers by running a generic Nginx container and mounting my api.conf file straight into the confd folder.
There we go. That's taking the api.conf file from my machine and mounting it straight in as confd. And now I can just expose port 80 and run the nginx container. So now I have api.com in my local etc hosts file pointing to my local host. So I can actually go to my browser and look at api.com/v1 and v2. There we go. API v1 is working and API v2 is working. If I stop v1, v2 continues to work just fine, and v1 will not work once that container stops. There we go. v1 you can see is just spinning and spinning and doesn't work, whereas v2 still works just fine. So it's an easy way to version out versions you no longer support. Keep them running as long as you want, don't maintain them, don't worry about them, and release your new versions, and eventually scale off the old versions simply by removing the containers. The multiple running versions deployment strategy is an extremely simple solution to help you get around some complicated problems that would otherwise mean a lot of code living in one repository or one application codebase, and it gives you that flexibility again to be able to use multiple technologies as the different versions go, evolving that program and not having to worry about causing any breaking damages to older versions. Congratulations, you've completed the course on using Docker. And along the way, I hope you learned some things. I hope you got the principles of scaling containerized architecture, some good ideas and some bad practices to avoid. But I hope you got those concepts, goals, and ideas, and also an understanding of how to go out and do it in real life. I hope your confidence grew that you can take Docker and build a real production application with it for your next application. So where do you go from here? Here's things that you should definitely do if you're interested in using Docker. 1. Use Docker. You will learn more from using it in the real world than from taking multiple courses. While courses definitely offer experience and great ideas, as well as best practices and bad practices to avoid, using Docker will give you experience you cannot get any other way. I'd encourage you, if you're at all interested in using it, just use it. Put it on a project and get it out there in the wild. Next up, join the community. Forums.docker.com is a great place to ask questions. People love to answer them as well, and get a part of a Docker meetup if there's one in your area. And lastly, join a conference. DockerCon or Velocity put on by O'Reilly are great conferences for people who are interested in DevOps and server administration. I hope you had a great time with this course, and thanks again for taking it, and great luck learning Docker.